Parkinson's Law. You have 2 weeks to finish a report. Day 1, you open the file. You glance at the outline. Plenty of time, you think. By day 10, barely a paragraph. Then the deadline closes in. Suddenly, in 48 hours, the whole thing's done. Not because the work was hard, because the time was there. Work expands to fill the time available for its completion. That's Parkinson's Law. Give yourself a month for a task that could take a week. You'll use the entire month. The work doesn't get more complex. You just stretch it out. Hesitation, revision, distraction, anything but finishing. The mechanism is simple. No pressure, no urgency. No urgency, no focus. You check emails. You tweak formatting. You tell yourself you're being thorough. Really, you're burning time. The task just sits there. It gets heavier not because it's difficult, but because the deadline hasn't forced you to compress it yet. It happens everywhere. Meetings scheduled for an hour run an hour, even if the actual decision takes 10 minutes. Budgets get spent because the money's there, not because the project needs it. Organizations expand staff to match funding, then justify the expansion by creating new processes that need more staff. The cycle feeds itself. Parkinson's Law doesn't just apply to tasks. It applies to entire systems. Bureaucracies grow because time and resources let them. Committees form subcommittees. Reports generate follow-up reports. The original purpose fades, but the structure stays sustained by the space it's been given. The law reveals something uncomfortable. Efficiency isn't natural. Left alone, work drifts toward complexity and delay. Only when constraints tighten, when time runs out or resources shrink, that's when focus sharpens. That's when waste gets cut. The report gets done in 2 days not because you suddenly became more capable. The absence of time forced clarity. No room for second guessing. No space for endless refinement. Just the task and the deadline, compressed into something that actually moves. Time doesn't just measure work. It shapes it. And when there's too much of it, the work stops being work. It becomes a way to fill the void. Murphy's Law. The presentation is in 10 minutes. You've rehearsed. The slides are ready. Then the projector dies. Or the file won't open. Or your laptop decides right now is the perfect time to install updates. It's not bad luck. If something can go wrong, it will. And it happens at the worst possible time. That's Murphy's Law, not superstition. It's how systems break under pressure. The more complex a process, the more points of failure. And the more critical the moment, the more those failures show themselves. A projector that worked yesterday fails today, because today it matters. The principle comes from aerospace engineering. Captain Edward Murphy, working on rocket sled experiments, watched a technician wire sensors wrong. His reaction wasn't anger. It was clarity. If there's a way to do something wrong, someone will eventually do it that way. The statement became a rule. Plan for failure. Failure doesn't need intention. It just needs opportunity. What makes Murphy's Law feel personal is timing. Failures don't spread evenly. They cluster around moments that matter. The toast doesn't always land butter side down. But when you're late, wearing a clean shirt, rushing out the door, that's when it does. Not because the universe has it out for you. Because that's when you notice. It shows up everywhere. Software launches. The system runs perfectly in testing. Then real users flood in, everything crashes. Travel. Flight delays pile up on the day you can't afford to miss. Relationships. The misunderstanding lands right before the important conversation. Complexity and pressure meet. Something gives. The law doesn't say everything will fail. It says vulnerabilities surface when stakes rise. The more variables in play, the higher the chance one of them breaks. A chain with 100 links only needs one weak point. A process with 10 steps only needs one error. The system doesn't have to collapse entirely. It just has to fail at the moment failure costs the most. Murphy's Law isn't pessimism. It's structural awareness. If a sequence depends on everything going right, it's fragile. Fragile systems don't survive contact with reality. The presentation fails not because you didn't prepare. The chain of dependencies had too many places to break. Laptop, cable, projector, software. Too many points of failure. The response isn't to expect disaster. It's to account for it. Backup plans, redundancies. Margin for error, not because failure is guaranteed, but because it's possible, and possibility is enough. The one time you don't prepare is the time it happens. Murphy's Law doesn't predict the future. It just reminds you the future has more ways to go wrong than you planned for. Goodhart's Law. The numbers look perfect. Every metric is up. Customer satisfaction scores at all-time highs. Response times drop to record lows. The dashboard glows green across every measure. Management celebrates. Then someone checks the actual customers. They're furious. Wait times feel endless. Problems go unsolved. What happened? When a measure becomes a target, it stops being a good measure. That's Goodhart's Law. The moment you make a metric the goal, people optimize for the metric, not the thing it's supposed to measure. And the gap between the number and reality starts to grow. The mechanism is deceptively simple. Measure something, people will find ways to improve that specific number. Not necessarily the underlying reality. Just the number. A hospital reduces patient wait times by redefining what counts as waiting. A school boosts test scores by teaching to the test, not teaching students to think. A call center shortens average call duration by hanging up on difficult questions. The metric moves. The mission dies. It's everywhere once you see it. Police departments judge officers by arrest numbers, so arrests go up for minor offenses while serious crimes get less attention. Social media platforms measure engagement, so algorithms amplify outrage and conflict because that's what keeps people scrolling. Companies track employee hours, so people stay late doing nothing just to be seen. The number becomes the performance. The performance becomes hollow. Goodhart's Law doesn't just distort individual behavior. It corrupts entire systems. When teachers are evaluated by student test scores, education becomes test preparation. When doctors are judged by patient throughput, care becomes an assembly line. When publishers chase click, journalism becomes clickbait. The measure was supposed to guide improvement. Instead, it becomes a game to win. The danger isn't the metric itself. It's what happens when the metric replaces the mission. You wanted better customer service, so you measured response time. Now your team responds fast with useless answers. You wanted employee productivity, so you tracked hours worked. Now people perform presence instead of output. You wanted quality content, so you measured shares. Now you get rage bait and misinformation. The original intent vanishes. What remains is a system perfectly optimized for something nobody actually wanted. All because you told people the number mattered more than the reason you started counting in the first place. Goodhart's Law is a warning. Measure what you value, but never mistake the measurement for the value itself. Because the moment you do, you'll get exactly what you measured, and nothing you actually needed. Pareto Principle. You finally got the promotion. Senior developer to team lead. Years of excellent code, solved every technical challenge thrown at you, now you're managing 5 people. 3 months in, you're drowning. Meetings you don't understand. Decisions you're not equipped to make. The work that made you great at your old job means nothing here. And slowly, quietly, you realize you've reached your ceiling. In every hierarchy, people rise to their level of incompetence. That's the Pareto Principle. You get promoted because you're good at your current job, not because you'll be good at the next one. Eventually, you land in a role where you can't excel. And there you stay, stuck at the level where you finally stop being competent. The pattern is brutally consistent. The best salesperson becomes a sales manager and struggles, because selling and managing are different skills. The brilliant teacher becomes a principal and flounders, because teaching students and running a school require opposite strengths. The gifted engineer becomes a director and fails, because technical mastery doesn't translate to organizational leadership. Each promotion rewards past performance. Each new role demands different abilities. Organizations accelerate this by design. Promotion is the only reward for doing well. So the star performer moves up, even when moving up means moving away from what made them valuable. There's no path that says stay here, keep doing what you're great at, we'll pay you more for it. The only direction is up. And up eventually means incompetent. The principle explains why so many managers are bad at managing. They weren't hired to manage. They were promoted for doing something else well. The company needed a manager, looked at who was great at the thing being managed, and assumed competence would transfer. It didn't. Now the organization has lost a great individual contributor and gained a mediocre leader. Everyone loses. It compounds over time. The incompetent manager can't identify talent below them because they don't understand the work anymore. So they promote based on the wrong signals, which creates more incompetent managers. The cycle continues until entire layers of the organization are staffed by people who used to be good at jobs they no longer do. The Pareto Principle isn't about failure. It's about structure. A system that rewards competence with promotion will inevitably fill its upper ranks with incompetence. Not because people are incapable, because they're capable of something else, something the organization no longer asks them to do. You don't rise to the top. You rise until you stop rising. And the place you stop isn't where you shine. It's where you finally meet a role you can't grow beyond. Hanlon's razor. They didn't reply to your message. You sent it hours ago. You know they saw it. They're online. They're posting. But your message just sits there, ignored. The anger builds. They're doing this on purpose. It's deliberate. A message. Disrespect. Except it's probably not. They just forgot. Or got distracted. Or didn't think it needed a response. Most harm isn't malice. It's carelessness. Never attribute to malice what can be adequately explained by stupidity. That's Hanlon's razor. Not stupidity in the cruel sense. Just human error, distraction, incompetence. The world is full of people making mistakes, forgetting things, misunderstanding situations. Malice is rare. Mess-ups are constant. The difference matters because we default to the wrong explanation. Someone cuts you off in traffic. Your first thought isn't they didn't see you. It's they're an aggressive driver who doesn't care. A colleague misses a deadline. You think they're sabotaging the project. Really, they just mismanaged their time. Your friend forgets your birthday. You assume they don't value you. More likely, they're overwhelmed and it slipped their mind. Malice requires intent, planning, sustained effort. Most people are just trying to get through the day without screwing up too badly. And they screw up anyway. Hanlon's razor cuts through the conspiracy. The company didn't reject your application to spite you. The system filtered it by keywords you didn't include. The neighbor didn't steal your package. It was delivered to the wrong address. The coworker didn't take credit for your idea to undermine you. They genuinely forgot you mentioned it first. Assuming malice makes you paranoid. Assuming incompetence makes you realistic. This isn't about excusing bad behavior. Some harm is intentional. Some people are malicious. But they're the minority. Most damage comes from people who didn't think, didn't check, didn't realize the impact of what they were doing. They're not villains. They're careless. And carelessness does plenty of harm on its own. The trap is that malice feels more satisfying to believe. If someone hurt you on purpose, it means you mattered enough to target. If they hurt you by accident, you're just collateral damage in their chaos. Malice gives you an enemy. Incompetence gives you randomness. But randomness is the truth most of the time. Hanlon's razor doesn't make the harm hurt less. It just stops you from wasting energy fighting battles that don't exist. They didn't betray you. They forgot. They didn't insult you. They phrased it badly. They didn't ignore you. They're bad at replying. Most of the time, people aren't thinking about you at all. And that's not malice. That's just how distracted, overloaded, imperfect humans operate. Assume incompetence first. You'll be right more often than you expect. Occam's razor. The project failed. You start building explanations. Maybe the vendor sabotaged it because they're trying to lock you into a new contract. Or the stakeholder had hidden political motives. Or there's a coordinated effort to make your department look bad. The explanation grows. More connections. More players. More moving parts. But the simple answer is right there. The requirements were unclear, the timeline was unrealistic, and no one wanted to admit it until it was too late. The simplest explanation is usually correct. That's Occam's razor. When you're choosing between competing explanations, the one that requires the fewest assumptions is most likely true. Not always. But often enough that you should start there before building conspiracy theories. The principle works because complexity is expensive. Every additional assumption is another thing that has to be true for the explanation to hold. The more assumptions, the more chances for one of them to be wrong. Simple explanations don't require intricate coordination or hidden motives. They work with what's already in front of you. You hear it constantly. Someone's tired all the time. They build a theory about rare vitamin deficiencies or undiagnosed conditions. The simple answer is they're not sleeping enough. A relationship feels off. One person assumes cheating, hidden resentment, a slow unraveling. The simple answer is they've both been stressed and stopped communicating. A company's new policy seems Byzantine. Employees theorize political maneuvering or intentional sabotage. The simple answer is poorly thought-out execution by people who didn't anticipate consequences. Occam's razor doesn't mean the simple answer is always right. Sometimes the complex explanation is correct. Sometimes there is a conspiracy. Sometimes the rare condition is the real diagnosis. But those are exceptions. Most of the time, when you're stacking assumptions to make a theory work, you're wrong. The instinct to complicate comes from pattern seeking. Humans are wired to find connections even when none exist. A coincidence feels like evidence. A possibility becomes a probability. Before long, you've constructed an elaborate explanation held together by maybes and what-ifs. And it feels convincing because you built it to fit the facts. But that doesn't make it true. Occam's razor is a filter. When you catch yourself adding layers, stop. Strip it back. What's the explanation that doesn't need hidden variables or unlikely coordination? What's the answer that relies only on things you know are true? Usually that's where the truth is. Not buried in complexity. Sitting in plain sight. The project failed because execution was bad. They didn't text back because they were busy. The system isn't working because it was poorly designed, not because someone's out to get you. Simple explanations don't feel as interesting. They don't give you a villain or a grand narrative. But they're usually what's actually happening. Complexity is seductive. Simplicity is boring. But boring is where the answers are. Hofstadter's law. It always takes longer than you think. You know this. You've lived it. So this time you add buffer. Double the estimate. Maybe triple. You account for delays, interruptions, surprises. You build in margin. Then it still takes longer. Every single time. Hofstadter's law states that it always takes longer than you expect. Even when you take into account Hofstadter's law. The recursion is the point. You can't escape it by planning for it. Because the moment you adjust for delay, new delays appear. The law doesn't just describe poor estimation. It describes why estimation itself is broken. The problem is invisible complexity. You see the task. You don't see everything the task touches. Writing code isn't just writing code. It's debugging, testing, integration, documentation, deployment. Each step reveals new steps. Each dependency has dependencies. What looked like a clean path forward branches into a tree of unexpected work. And you didn't account for the branches because you didn't know they existed. Hofstadter's law compounds. You're halfway through, already behind schedule, so you rush. Rushing creates mistakes. Mistakes create rework. Rework takes time. Now you're further behind than if you'd gone slowly from the start. The delay feeds itself. It shows up everywhere. Home renovations that balloon from weeks to months. Product launches that slip from quarter to quarter. Books that take years instead of months to finish. The estimate isn't just wrong. It's structurally incapable of being right, because the work changes as you do it. New information appears. Requirements shift. Problems you couldn't have predicted become problems you have to solve. Adding buffer doesn't fix this. It just moves the failure point further out. You planned for delays. You get different delays. You budgeted for obstacles. New obstacles show up. The law holds because uncertainty doesn't compress. It expands. The more you learn about what you're doing, the more you realize you didn't know. Hofstadter's law isn't pessimism. It's structural honesty. Tasks are more complex than they appear from the outside. And the only way to discover that complexity is to start. By which point, you've already committed to an estimate that's wrong. You can't beat the law. You can only accept it. Stop trying to estimate perfectly. Start planning for the fact that you're going to be wrong. Because even knowing you'll be late doesn't make you on time. It just makes you less surprised when it happens. Brooks's law. The project is behind schedule. Deadlines are slipping. Management panics and does the obvious thing. Throws more people at it. More developers. More designers. More hands to share the load. 3 months later, the project is even more behind than before. What happened? Adding manpower to a late software project makes it later. That's Brooks's law. It sounds backwards. More people should mean more output. But it doesn't work that way. Because people aren't interchangeable units of productivity. They're coordination costs disguised as resources. The mechanism is communication overhead. Every new person added to a project has to be brought up to speed. That takes time from the people already working. They stop making progress to explain context, review code, answer questions. The more people you add, the more time gets spent on coordination instead of execution. A team of 5 has 10 communication channels. A team of 10 has 45. The work doesn't scale linearly. The complexity does. Then there's task dependency. Not all work can be parallelized. If 9 women can't make a baby in 1 month, 9 developers can't build interdependent systems any faster than 3. Some tasks have to happen in sequence. Adding people to sequential work just creates more people waiting for the bottleneck to clear. Brooks's law reveals a deeper truth about systems. Complexity grows faster than capacity. Double the team size, you don't double the output. You quadruple the coordination burden. Communication, integration, conflict resolution, all of it expands. Meanwhile, the actual work that needs doing stays the same size. You've just made it harder to do. This is why crisis reinforcement fails. The project is late because it's complex. Adding people makes it more complex. Now you're not just behind schedule. You're behind schedule with a bloated, uncoordinated team that can't move fast because everyone's stepping on everyone else. The problem you tried to solve got worse. Organizations keep making this mistake because the alternative feels like giving up. You can't add people, you can't speed up the timeline. What's left? Cutting scope. Simplifying the problem. accepting that some things won't get done. That's the actual solution. Not more resources, less ambition. Brooks's law is a warning about what doesn't scale. Effort scales. Coordination doesn't. And past a certain point, adding effort just adds coordination. Which means you're moving backwards while feeling productive. The project isn't late because you don't have enough people. It's late because the work is harder than you thought. And more people won't make hard work easier. They'll just make it more expensive to fail. Conway's law. Your product has 3 separate teams. Front-end, back-end, infrastructure. A year later, your system has 3 separate architectures that barely talk to each other. The front-end team built their own data layer. The back-end team built their own deployment tools. Infrastructure operates in a silo. Nobody planned it this way. But that's what you got. Organizations design systems that mirror their own communication structure. That's Conway's law. The architecture of your product reflects the architecture of your company. Not because anyone decided it should. Because it can't do anything else. The reason is simple. Teams build what they can build without coordinating. If 2 teams don't talk, they won't build integrated systems. They'll build separate systems with an interface between them. The cleaner the organizational boundary, the harder the technical boundary. Your org chart becomes your system diagram. You see it constantly. Companies with separate mobile and web teams end up with separate mobile and web codebases, even when they're solving the same problems. Companies organized by product line end up with siloed platforms that don't share infrastructure. Companies with regional divisions end up with regional systems that can't talk to each other. The organization shape dictates the software shape. Conway's law doesn't just apply to software. It applies to any output that requires coordination. If your marketing and sales teams don't communicate, your messaging will be inconsistent. If your design and engineering teams are separate, your products will feel like 2 different visions duct taped together. If leadership is fragmented, strategy will be fragmented. Structure creates output. The law works in reverse too. Want to build a unified platform? You need a unified team. Want seamless integration? You need teams that actually integrate. The software won't be more connected than the people building it. You can't organizational chart your way to technical excellence if the organizational chart is the problem. This is why reorganizations matter. Change the team structure, you change what gets built. Split a team, you create a split system. Merge teams, systems start converging. The code follows the people, always. Conway's law is a mirror. Your product is a reflection of how your company works. If you don't like what you see in the product, look at the organization. Because the architecture isn't a technical choice. It's an organizational inevitability. You can't fight Conway's law. You can only use it. Structure your teams the way you want your systems structured. Because one way or another they're going to match. Metcalfe's law. The first person to get a phone had a useless device. Nobody to call. The second person made it slightly valuable. 2 people can talk. The 10th person made it more useful. 100 people, suddenly it's essential. 1,000, and you can't function without it. The product didn't change. The number of connections did. The value of a network grows exponentially with the number of users. That's Metcalfe's law. Specifically, the value increases with the square of the number of participants. Not because the network gets better. Because every new user adds connections to everyone already there. 1 user, 0 value. 2 users, 1 connection. 10 users, 45 connections. 100 users, nearly 5,000. The math explodes. This is why social networks feel worthless at the start and indispensable later. When Facebook was just college students, it was a novelty. When it hit 1 billion users, it became infrastructure. Not because the features improved that much. Because everyone you know is there. The network became valuable by becoming inescapable. Metcalfe's law explains winner takes all dynamics. The bigger network is exponentially more valuable than the smaller one. So users migrate to the bigger one, making it even bigger, making it even more valuable. The gap doesn't shrink. It compounds. That's why dominant platforms are so hard to displace. It's not that they're better. They're bigger. And bigger means more valuable. And more valuable attracts more users. The loop self-reinforces. The law has a dark side. Early in a network's life, growth is everything. The product can be broken, the experience mediocre, the ethics questionable. Doesn't matter. Add users. Because once you hit critical mass, the network effect takes over. Users stay not because they like it, but because everyone else is there. You're not competing on quality anymore. You're competing on inevitability. This is why new platforms have to grow fast or die. If you don't reach critical mass before users drift away, you never will. Because a half-empty network has negative value. Joining a platform where nobody you know exists feels like joining a ghost town. So people leave. Which makes it more of a ghost town. Which makes more people leave. The same exponential curve that drives growth drives collapse. Metcalfe's law also explains why networks resist change. Every user has connections to other users. Changing platforms means losing those connections. The bigger the network, the more you lose by leaving. So people stay locked in. Not because switching is impossible. Because switching is expensive. The network becomes a cage built from your own relationships. The value isn't in the product. It's in the people using it. And once enough people are using it, the product becomes secondary. The network is the moat. The connections are the prison. And the law that made it valuable is the same law that makes it inescapable. Cunningham's law. You want to know how to do something. Center a div in CSS, configure a server, fix a weird bug. You ask online. Post the question clearly. Provide context. Wait. Hours pass. Maybe someone answers. Maybe not. Or you could just post the wrong answer confidently. Within minutes, 5 people will correct you. The best way to get the right answer on the internet isn't to ask a question. It's to post the wrong answer. That's Cunningham's law. Not because people are helpful. Because people love being right. And nothing motivates someone to share knowledge faster than seeing someone else be wrong in public. The mechanism is ego. Asking for help triggers sympathy. Maybe someone feels generous, maybe not. But posting something incorrect triggers correction instinct. You're wrong, they're right, they get to prove it. That's irresistible. The question dies in silence. The wrong answer spawns a thread of corrections within minutes. This isn't hypothetical. It's a documented pattern across every forum, subreddit, and comment section on the internet. A genuine question gets ignored. A confident but wrong statement gets demolished with detailed explanations of why it's wrong and what the right answer actually is. You don't even have to try. Just be wrong loudly. The internet will educate you out of spite. Cunningham's law reveals something uncomfortable about how information spreads. Accuracy doesn't drive engagement. Conflict does. A correct statement sits quietly. A wrong statement starts arguments. And arguments generate activity. So, platforms reward controversy, not correctness. The algorithm doesn't care if you're right. It cares if you're getting replies. This creates perverse incentives. If being wrong gets more attention than being right, why bother being right? Post something inflammatory. Get engagement. Correct yourself later if you feel like it. Or don't. The damage is done, the reach is achieved, and the correction will get a fraction of the visibility. Misinformation doesn't spread because people believe it. It spreads because it generates responses. The law works because certainty is a trigger. Someone states a fact incorrectly, and the urge to correct them overpowers the urge to scroll past. It's not about helping. It's about not letting wrongness stand. So the correction comes fast, often with links, sources, detailed explanations. Information you'd never volunteer to someone asking nicely, but will absolutely provide to prove someone wrong. Cunningham's law isn't a life hack. It's a diagnosis. The internet doesn't run on cooperation. It runs on the compulsion to correct. If you want knowledge, don't ask. Provoke. Because helping is optional, but being right is mandatory. Brandolini's law. Someone posts a lie. Takes them 10 seconds. Vaccines cause autism. The election was stolen. This miracle cure works. No sources. No evidence. Just a claim. Now you want to refute it. You need studies, data, context, expert testimony, historical precedent. You spend an hour writing a detailed rebuttal. They respond with another lie in 10 seconds. You're already behind. The amount of energy needed to refute misinformation is an order of magnitude larger than the energy needed to produce it. That's Brandolini's law, also called the bullshit asymmetry principle. Creating a lie is cheap. Debunking it is expensive. And that asymmetry is a weapon. The mechanism is burden of proof. The person making the claim doesn't have to prove anything. They just say it. But the person refuting it has to provide evidence, explain context, address every angle, anticipate counter-arguments. 1 sentence to lie. 5 paragraphs to explain why it's wrong. By the time you've finished, they've moved on to 3 new lies. You can't keep up. This is why misinformation spreads faster than correction. A lie fits in a headline. The truth needs an article. A conspiracy theory is exciting. The debunk is boring. A scary claim gets shared instantly. The fact check gets ignored. The emotional impact of the lie lands before the rational response can form. And once it lands, it's embedded. Correcting it later doesn't erase it. It just adds noise. Brandolini's law explains why bad actors win information wars. They're not trying to convince you the lie is true. They're trying to exhaust you. Flood the zone with so much garbage that debunking it all becomes impossible. You can't fact-check faster than they can fabricate. So eventually, you stop trying, and unopposed lies start sounding plausible just from repetition. Platforms accelerate this. Algorithms reward engagement, not accuracy. A dramatic false claim gets shares than a careful correction. The lie goes viral. The debunk gets a fraction of the reach. Even when corrections exist, they don't catch up. The audience that saw the lie never sees the truth. The asymmetry isn't just in effort. It's in distribution. The law also describes exhaustion as a strategy. Keep lying. Make them chase. Every refutation drains energy. Eventually, fact-checkers burn out. Journalists move on. The audience gets tired of hearing that's not true and starts wondering why there's so much smoke if there's no fire. The liar doesn't have to win the argument. They just have to outlast the truth-tellers. Brandolini's law is a structural advantage for dishonesty. Lying is fast, easy, and emotionally satisfying. Truth is slow, hard, and often boring. And in an environment that rewards speed and emotion, truth doesn't stand a chance. You can't beat the law by working harder. You beat it by changing the rules. Make the liar prove their claim instead of making the debunker disprove it. Stop amplifying lies just to correct them. Recognize that some fights aren't worth having, because refuting every lie is a losing game. And the person flooding the zone with garbage knows it. Campbell's law. Test scores are up. Graduation rates are climbing. Every metric shows improvement. Politicians celebrate. Schools get funding. Then you look closer. Students can pass tests but can't write essays. Graduation rates rose because standards dropped. The numbers got better. Education got worse. The more a metric is used for decision-making, the more it becomes corrupted, and the more it corrupts the process it's meant to measure. That's Campbell's law. Similar to Goodhart's law, but darker. It's not just that the metric stops being useful. It actively destroys the thing you're trying to improve. The corruption happens in layers. First, people optimize for the metric instead of the goal. Teachers teach to the test instead of teaching students to think. Then the metric itself gets gamed. Schools push struggling students to drop out before test day to protect their scores. Finally, the entire system reorganizes around maintaining the metric, even when it contradicts the original mission. Education becomes test preparation. Healthcare becomes patient throughput. Policing becomes arrest quotas. Campbell's law explains why metrics-driven reform often backfires. You want better schools, so you measure test scores. Schools optimize for test scores by narrowing curriculum, teaching test-taking strategies, and sometimes outright cheating. The metric improves. Learning declines. But the numbers say success, so the policy continues. The law accelerates when stakes rise. Low-stakes metrics get ignored. High-stakes metrics get corrupted. Taitika pay to test scores, suddenly test scores are unreliable. Hospital funding to patient satisfaction. Hospitals start over-prescribing pain medication to boost ratings. Police performance to crime statistics become fiction. The higher the stakes, the faster the corruption. This creates perverse institutional behavior. Organizations know the metric is flawed. But they're evaluated on the metric, not on reality. So they manipulate the metric while letting the underlying problem fester. Crime doesn't drop. It just stops getting reported. Hospitals don't improve care. They improve scores. Schools don't educate better. They test better. Campbell's law is Goodhart's law with consequences. Goodhart says the metric stops working. Campbell says the metric starts destroying. The measurement becomes the mission. The mission becomes irrelevant. And everyone involved knows it's happening but can't stop, because the system runs on the corrupted metric. You can't fix this by finding better metrics. Any metric under pressure will corrupt. The fix is removing the pressure. Stop using single numbers to make complex decisions. Stop incentivizing the measure instead of the outcome. Because the moment measurement becomes control, measurement becomes lies. Sayre's law. The meeting has been going for an hour. The topic is which font to use in the company newsletter. Voices are raised. Positions are entrenched. Someone threatens to escalate to leadership. Meanwhile, the actual strategic decisions, the ones that determine whether the company survives, got nodded through in 10 minutes with barely any discussion. In any dispute, the intensity of feeling is inversely proportional to the value of the issues at stake. That's Sayre's law. The smaller the stakes, the bigger the fight. Trivial matters generate fierce conflict. Critical matters get quiet consensus. The mechanism is accessibility. Everyone has an opinion on fonts, paint colors, meeting schedules. Not everyone can evaluate complex strategy, technical architecture, or long-term risk. So people engage where they feel competent, which means they engage on the trivial. The font debate becomes a proxy battle for influence because it's something everyone can understand and fight about. You see this everywhere. City councils spend hours debating the design of a bike rack and minutes approving million-dollar infrastructure projects. Academic departments wage bitter wars over office space while fundamental research directions pass without objection. Online communities have calmer discussions about existential topics than about moderation policies. Sayre's law explains why small decisions feel so contentious. There's no external constraint forcing resolution. A major decision has deadlines, budget limits, real consequences that force compromise. A trivial decision has none of that. So it becomes an endless argument where people can indulge every preference and grievance without cost. The debate drags on because nothing forces it to end. The law also reveals power dynamics. When people can't influence things that matter, they fight harder over things that don't. It's psychological compensation. You can't change the company's direction, but you can fight about the newsletter font. That fight feels like control. even though it's control over nothing. This creates organizational dysfunction. Leadership thinks letting people debate small things gives them voice and ownership. Instead, it trains them to waste energy on irrelevance. The real decisions happen elsewhere, in rooms where voices aren't raised, because the stakes are high enough that people act professionally. The shouting matches happen over trivia. Sayre's law is a diagnostic. If the argument is fierce, the stakes are probably low. If it matters, the discussion is usually calmer. Not because important things don't generate disagreement, but because important disagreements force people to engage seriously instead of emotionally. The solution isn't to make trivial decisions quickly. It's to recognize when a fight is trivial and stop investing energy in it. Because the font doesn't matter, and acting like it does just means you're not paying attention to what actually does. Sturgeon's law. 90% of everything is crap. Books, movies, music, art, ideas, products. Doesn't matter the field. Doesn't matter the era. Most of it is mediocre at best, terrible at worst. That's Sturgeon's law. And it's not pessimism. It's math. The law emerged from a defense of science fiction. Critics claimed the genre was mostly garbage. Theodore Sturgeon responded that 90% of everything is garbage. Science fiction wasn't worse than other genres. It just had the same distribution. Most things are bad. A few things are good. Excellence is rare. The ratio holds because production is cheap and standards are hard. Anyone can write a book. Publishing a book takes effort. Writing a good book takes talent, skill, and time. Most people have the first. Few have all three. So most output is bad. Not because creators are incompetent. Because good work is difficult and most attempts fall short. Sturgeon's law explains content overload. The internet didn't create bad content. It removed gatekeepers. When anyone can publish, they do. The total volume explodes. The ratio stays the same. 90% of YouTube videos, blog posts, podcasts, and tweets are forgettable. The other 10% justify the platform's existence. But you have to wade through the 90 to find the 10. The law applies to products too. Most new businesses fail. Most apps get deleted. Most inventions don't work, not because entrepreneurship is broken. Because most ideas are mediocre, most execution is flawed, and most timing is wrong. The successful 10% look inevitable in retrospect. They weren't. They were the minority that survived contact with reality. This creates a filtering problem. If 90% is crap, how do you find the 10% that isn't? You can't evaluate everything. There's too much. So you rely on filters. Critics, recommendations, algorithms, reputation. And those filters have their own biases, blind spots, and failures. Which means some of the good 10% gets buried with the bad 90. And some of the bad 90 gets elevated by luck or manipulation. Sturgeon's law isn't a reason to give up. It's a reminder that quality is scarce. When you find something good, it's an outlier. When you produce something good, you've beaten odds. The default state is mediocrity. Excellence is the exception. The law also means you can ignore most things. If 90% is crap, you're not missing much by skipping it. The fear of missing out assumes everything might be valuable. Sturgeon's law says most things aren't. So be selective. Most of what you're not seeing isn't worth seeing. 90% of everything is crap, which means the remaining 10% is where all the value is. And that 10% is enough. Amara's law. When the internet arrived, people thought it would change everything immediately. Every business would go online. Every transaction would be digital. The future was now, except it wasn't. Adoption was slow. Infrastructure lagged. Most of the promised revolution didn't materialize for years. Then, quietly, it did. And it was bigger than anyone predicted. We overestimate the effect of technology in the short run and underestimate it in the long run. That's Amara's law. The hype cycle gets it backwards. The first 2 years, nothing happens. The next 20 years, everything does. The pattern repeats with every major technology. The internet, mobile phones, artificial intelligence, blockchain. Launch triggers massive hype. Expectations skyrocket. Then reality hits. The technology is clunky. Adoption is slow. Use cases are unclear. Disillusionment sets in. People declare it overhyped, a fad, dead on arrival. Meanwhile, the technology is quietly improving, integrating, becoming infrastructure. By the time people stop paying attention, it's reshaping everything. Amara's law explains why predictions fail. Short-term predictions assume rapid adoption and ignore friction. New technology faces resistance from existing systems, user habits, regulatory barriers, and simple inertia. Change is slow because it requires everything else to change too. So the revolution doesn't happen in 2 years. It happens in 10 or 20. By which point, the revolution is so embedded you forget it was ever revolutionary. The law also describes how technology becomes invisible. In the short run, it's a novelty. Everyone talks about it. In the long run, it's infrastructure. Nobody talks about it because it's just how things work. Electricity was revolutionary. Now it's background. The internet was transformative. Now it's assumed. Smartphones reshaped society. Now they're boring. The most impactful technologies are the ones you stop noticing. This creates strategic errors. Companies overinvest in the short-term hype and underinvest in long-term integration. They chase the revolutionary use case that doesn't exist yet and ignore the incremental improvements that compound into transformation. By the time the long-term impact arrives, they've moved on to the next hype cycle. Amara's law is also why incumbents fail. They see the new technology, dismiss it as overhyped because it doesn't immediately disrupt them, then get blindsided years later when the long-term effects kick in. Kodak saw digital cameras. Too slow, too expensive, too niche. By the time digital became dominant, Kodak was irrelevant. The threat wasn't immediate. That's what made it fatal. The law reverses too. Overhype in the short run creates underhype in the long run. When the initial excitement fades and the technology doesn't deliver immediately, people assume it never will. They stop paying attention. Which means they miss the moment when it actually starts mattering. Amara's law is a timing problem. We're impatient for revolution and blind to evolution. The short run is loud and disappointing. The long run is quiet and transformative. And by the time you realize the transformation happened, it's already too late to catch up. Tesler's law. The app got simpler. One-click checkout. Autofill forms. Recommendations that just work. The interface is clean, intuitive, effortless. Meanwhile, behind the scenes, the system is a nightmare. Hundreds of microservices, machine learning models, complex data pipelines, edge case handling everywhere. The user experience got easier. The engineering got exponentially harder. Complexity doesn't disappear. It moves. That's Tesler's law, the law of conservation of complexity. Every system has a certain amount of inherent complexity that can't be removed. You can only decide who deals with it, the user or the builder. The trade-off is simple. Make it easier for users, it gets harder for developers. Make it easier for developers, it gets harder for users. There's no escaping the complexity. Just shifting it around. A simple interface requires complex code. Simple code produces a complex interface. You don't reduce complexity. You redistribute it. This explains why great products feel effortless. They are effortless for the user. Someone else absorbed the complexity. Autocorrect doesn't just fix typos. It predicts intent, understands context, learns patterns. That's thousands of engineering hours compressed into a feature that feels obvious. The simplicity is an illusion. The complexity is hidden. Tesler's law applies beyond software. Customer service that feels seamless requires complex back-end systems and trained staff. Fast delivery requires elaborate logistics networks. Easy returns require reverse supply chains. Every convenience you don't think about is a system someone built to handle complexity you don't see. The law creates strategic choices. Do you optimize for user experience or developer velocity? You can't fully optimize both. Make the interface dead simple, you slow down development because every feature requires extensive edge case handling. Keep the codebase simple. Users have to deal with quirks and limitations. Most products pick one and accept the trade-off. This is why just make it simpler is naive advice. Simpler for who? The user or the builder? Because making it simpler for one makes it more complex for the other. The complexity is fixed. You're just deciding where it lies. Tesler's law also explains technical debt. Teams take shortcuts to ship faster. They push complexity onto users. Confusing interfaces, manual workarounds, inconsistent behavior. Later, they try to clean it up, pull complexity back into the system. But that complexity still exists. It's just moving from user pain to engineering effort. The total amount hasn't changed. The law doesn't mean you're stuck with complexity. It means you can't eliminate it. You can only manage it. Decide where it should live. Invest in absorbing it where it matters. Accept it where it doesn't. But don't pretend you're making it disappear. You're just choosing who pays the cost. Complexity is conserved. It shifts between user and system, between interface and implementation, between now and later. But it never goes away. And anyone promising otherwise is just moving it somewhere you're not looking yet. Gall's law. You're designing the perfect system. Everything planned from the start. Complete architecture. Every module specified. All edge cases handled. It's comprehensive, elegant, ready to build. Then you build it. And it doesn't work. Because complex systems designed from scratch never do. A complex system that works is invariably found to have evolved from a simple system that worked. That's Gall's law. You can't design complexity up front. You have to grow it. Start simple. Make it work. Then expand. Trying to build the final version first guarantees failure. The reason is unknowns. You don't know what you don't know until you build something and watch it fail. Every complex system has hidden dependencies, emergent behaviors, and unforeseen interactions. You can't predict them in a design document. You discover them in operation, and you can't discover them until you have something running. This is why grand redesigns fail. The team looks at the messy existing system, decides to rebuild it properly this time, and creates a comprehensive plan. Then they build it. And it doesn't work the way the old system worked. Because the old system, for all its flaws, evolved through contact with reality. The new system was designed in isolation. It has no immune system for real-world cows. Gall's law explains successful systems. They didn't start complex. They started minimal. Solve one problem. Make that work. Add another piece. Make that work. Iterate. Each addition is small enough to understand, test, and fix. Over time, the system grows complex. But it works at every stage. Complexity emerges from simplicity that functions. It can't be imposed from nothing. The law applies to organizations too. You can't design the perfect company structure up front. You start small. A few people solving a problem. It works. You hire more people. Adjust the structure. It works. You scale. Adjust again. The organization evolves. Trying to implement a complex org chart from day one creates dysfunction, because the structure has no relationship to how the work actually happens. Gall's law is why startups beat established companies at innovation. Startups start simple. They build the minimum thing that works, ship it, learn from it, iterate. Established companies try to design the perfect solution up front. Committees, requirements, documents, comprehensive planning. By the time they ship, the market has moved and the design assumptions are wrong. The simple system that's shipped beats the complex system that's still in planning. The law is a process constraint. You can't skip steps. You can't go from nothing to complex and have it work. You have to go from nothing to simple, make that work, then layer on complexity gradually. Each layer validated before the next. Violate this, and you get an expensive system that doesn't function because it was never grounded in working simplicity. Gall's law isn't about lowering ambition. It's about sequencing. Build the complex thing you want. But build it by evolving simple things that work, not by designing the end state first. Because the end state you design won't be the end state that works. Reality will change it. Better to discover that incrementally than catastrophically. Start simple. Make it work. Then grow. Anything else is fantasy. Hyrum's law. You're fixing a bug in your API. A small change. Harmless. You ship it. Immediately user systems break. Turns out they weren't using the API the way you documented. They were relying on a quirk. A timing issue. An undocumented side effect. You never promised that behavior. But they built on it anyway. Now you can't change it without breaking them. With a sufficient number of users, every observable behavior of your system will be depended on by somebody. That's Hyrum's law. It doesn't matter what you intended. It doesn't matter what you documented. If users can see it, someone is using it. And once they're using it, it becomes a contract you can't break. The mechanism is surface area. Every aspect of a system that's visible is a potential dependency. Return order. Error messages. Timing. Performance characteristics. Even bugs. Users don't just depend on what you say the system does. They depend on what it actually does. And what it actually does is everything they can observe. This is why legacy systems are impossible to change. Not because the code is bad. Because users have built on every observable detail. Change the error message format, someone's parser breaks. Fix a timing bug, someone's workaround stops working. Improve performance, someone's rate-limiting logic fails. The system isn't just the documented interface. It's every behavior that exists. Hyrum's law explains API paralysis. You want to improve the system. Clean up inconsistencies. Remove deprecated features. But you can't. Because someone somewhere is depending on exactly that inconsistency, that deprecated feature, that weird behavior you never intended. And breaking them is breaking your contract, even though you never promised it. The law compounds over time. More users means more dependencies. More dependencies means less flexibility. Eventually, you're locked into behaviors that were never designed, never documented, never intended. They're just artifacts of implementation that became load-bearing because someone built on them. This creates a ratchet effect. You can add behaviors. You can rarely remove them. Every addition is permanent because once it's observable, it's depended on. The system grows more complex not because you're adding features, but because you can't remove anything. Technical debt becomes permanent because paying it down means breaking users. Hyrum's law isn't about bad users. It's about emergent behavior at scale. With enough users, every edge case gets hit. Every quirk gets relied on. Every implementation detail becomes a feature. Not because users are trying to break things. Because they're using what's there. And what's there is everything they can see. The solution isn't better documentation. Users will depend on undocumented behavior anyway. The solution is designing for change from the start. Minimize observable surface area, version everything. Deprecate gradually. Because once behavior escapes into the wild, it's yours forever, intended or not. Little's law. The restaurant is packed. Tables full. Line at the door. You've been waiting 20 minutes. More people keep arriving. The wait keeps growing. Management panics. Adds more tables. Hires more servers. Somehow, the wait gets worse. What's happening? The number of items in a system equals the rate they arrive multiplied by the time they spend there. That's Little's law. Sounds abstract. It's not. It's how Cayuse work, and it explains why adding capacity doesn't always reduce wait times. The math is simple. If 10 customers arrive per hour and each stays for 2 hours, there are 20 customers in the restaurant at any time. Want fewer customers waiting? Either reduce arrivals or reduce how long each one stays. Increase capacity without changing those. You've just made room for more people to wait longer. Little's law explains why scaling doesn't solve congestion. Add lanes to a highway, more cars show up. Traffic doesn't improve because you didn't change arrival rate or time spent. You just created more space to be stuck in. Same with customer service. Add more agents, customers call more often because wait times drop initially, then equilibrium reestablishes at the same wait. The law reveals hidden bottlenecks. You think the problem is capacity. More tables, more servers, more space. But if customers are staying longer because service is slow, adding tables just means more people waiting for slow service. The bottleneck isn't space, it's throughput. And throughput is determined by how long things stay in the system. This is why checkout lines work differently than you expect. One long line feeding multiple registers is faster than multiple short lines. Not because total capacity changed, because time in system is more predictable. Nobody gets stuck behind the person with a complicated transaction. The variance drops. Average time drops. The Cayuse shrinks even with the same number of registers. Little's law applies beyond physical Cayuse. Software systems, project workflows, manufacturing. Anywhere things arrive, get processed, and leave. If work is piling up, you have 3 options. Reduce arrival rate, speed up processing, or accept that the Cayuse will keep growing. There's no 4th option. The math doesn't allow it. The law also explains why just work faster fails. Speed up processing but arrivals increase to match, you're back where you started. The system finds equilibrium. The only way to permanently reduce Cayuse size is to change the ratio. Fewer arrivals per unit time or faster processing per item. Anything else is temporary. Little's law is a constraint. You can't trick it. You can't work around it. The Cayuse size is determined by arrival rate and time in system. Change one or both, or the Cayuse stays the same. Add more capacity without changing those. You've just built a bigger waiting room. Amdahl's law. You have a task that takes 10 hours. Half of it can be parallelized across multiple workers. The other half has to happen sequentially. You throw 10 workers at it. You expect it to finish in maybe 2 hours. It finishes in 5.5. What happened? The speed up from parallelization is limited by the portion of the task that must be sequential. That's Amdahl's law. You can't parallelize your way out of serial work. And the serial work determines your maximum possible speed up, no matter how many resources you add. The math is brutal. If half the work is sequential, the maximum speed up is 2 times, no matter how many workers you have. 1 worker, 10 workers, 1,000,000 workers doesn't matter. The sequential half sets the floor. You can make the parallel part instant. You still have the sequential part to do. And that's your limit. Amdahl's law explains why adding resources has diminishing returns. First few workers give decent speed up. Then each additional worker contributes less. Eventually, you're adding workers who have nothing to do because they're all waiting for the sequential part to finish. More workers, same completion time. You've hit the law's ceiling. The law applies to everything, not just computing. A project has sequential dependencies. Design before implementation. Testing after development. You can parallelize implementation across a team. But design is sequential, so is testing. Add more developers, you speed up implementation. But the overall project time is still bound by design and testing. The sequential phases dominate. This is why some problems don't scale with resources. You can't make a baby in 1 month with 9 women. Pregnancy is sequential. No amount of parallelization changes that. Same with any task that has inherent ordering. The sequential portions set the limit. Everything else is just filling time around them. Amdahl's law creates a strategic problem. You want to speed things up. You can't reduce the sequential work, so you paralyze everything else. But that's expensive. More workers, more coordination, more overhead. And you're chasing diminishing returns because the sequential portion still dominates. You spend more to get less. The law also explains optimization priorities. If 90% of your task is sequential, paralyzing the remaining 10% gives minimal speed up. You should optimize the sequential part instead. But that's often harder. Parallel work is easy to scale. Just add resources. Sequential work requires fundamental changes to how the work is structured. So teams optimize the wrong thing because it's easier. Amdahl's law is a ceiling. Parallelization can only take you so far. Past that, you're hitting the wall of sequential work, and no amount of resources can break through. The speed-up is capped. The law doesn't care how much you invest. It cares about the structure of the work. And some structures don't parallelize. Moore's law. Every 2 years, the number of transistors on a chip doubles. For decades, this held true. Computers got faster. Phones got smarter. Technology advanced on a predictable curve. Then the curve started bending. Physics caught up. Heat, power, quantum effects. The doubling slowed. But the expectation didn't. Moore's law wasn't a law of physics. It was a prediction, a target, and for a long time the industry organized itself to meet it. Roadmaps aligned. Investment followed. R&D pushed boundaries. The law became self-fulfilling because everyone believed it. Until they couldn't make it true anymore. The mechanism was coordination. Chip manufacturers, software developers, hardware makers, all planned around Moore's law. New chips would be twice as fast in 2 years. So design for that. Build for that. Wait for that. The industry moved in lockstep. And because everyone expected the doubling, everyone worked to make it happen. Moore's law shaped entire industries. Software got bloated because hardware would catch up. It'll be fast enough in 2 years. Applications that were too slow shipped anyway. Games that required future hardware launched with minimum spec requirements nobody could meet yet. The law gave permission to build for tomorrow's performance, not today's. Then the law broke. Not suddenly. Gradually. The doubling slowed to every 3 years. Then 4. Heat became a problem. Power density hit limits. Transistors got so small that quantum tunneling started interfering. Physics imposed constraints that engineering couldn't overcome. The curve bent. The industry kept expecting it to continue. It didn't. This created a gap. Software assumed hardware would keep accelerating. Hardware couldn't. Performance gains stalled. Suddenly, efficiency mattered again. Code that was slow but didn't matter because next year's chip would make it fast became a problem. The free lunch was over. Developers had to optimize again. An entire generation had never needed to. Moore's law also explains why old assumptions die hard. For 50 years, the law held. An entire industry internalized it. Wait for faster hardware. Don't optimize too early. The next generation will solve it. When the law stopped holding, the habits remained. Companies kept designing for performance gains that weren't coming. The mismatch created lag. The law's end didn't kill progress. It shifted where progress happens. Instead of raw speed, now it's efficiency, architecture, specialization, parallel processing. The curve didn't stop. It changed shape. But the mental model, the expectation of exponential improvement, that took longer to update. Beliefs persist even when reality shifts. Moore's law was never inevitable. It was a coordination mechanism wrapped in a prediction. And it worked because everyone acted like it was true. which made it true, until the physics said no. Now the challenge isn't making chips faster. It's unlearning the assumption that they will be. Wirth's law. You buy a new computer, faster processor, more memory, better everything. You install the same applications you used before. Somehow they feel the same speed, or slower. The hardware doubled in power. The software got heavier. You're running to stay in place. Software gets slower faster than hardware gets faster. That's Wirth's law, named after computer scientist Nicholas Wirth, who watched software bloat consume every hardware gain. The trend is relentless. Computers get more powerful. Software gets more inefficient. The user experience stays roughly the same. The mechanism is abundance. When resources are scarce, developers optimize. When resources are plentiful, they don't. More memory means loading more libraries. Faster processors mean tolerating inefficient code. Better graphics mean adding more effects. Every hardware improvement gets absorbed by software that takes advantage of it. Not through better features, through heavier implementation. Wirth's law explains why old software on old hardware often feels snappier than new software on new hardware. A word processor from the 90s started instantly on its contemporary machine. A modern word processor takes seconds to load on a machine 1,000 times more powerful. The old one was optimized for constraints. The new one is built for abundance, and abundance gets wasted. The law compounds through layers. Operating systems get heavier. Frameworks get heavier. Applications get heavier. Each layer assumes the layer below will be fast enough. Nobody optimizes because the hardware will compensate. Except every layer thinks that. So every layer adds weight, and the sum of all that weight consumes the hardware gains. This creates a treadmill. Hardware advances. Software expands to fill the space. Users see minimal improvement, so they demand better hardware, which enables heavier software. The cycle continues. Performance doesn't improve. Capacity just gets reallocated to bloat. Wirth's law isn't inevitable. It's a consequence of incentives. Optimizing software takes time. Waiting for faster hardware is easier, so developers wait. And hardware manufacturers keep delivering. As long as that cycle continues, software will consume every hardware gain. The law also explains why some tools feel fast despite being old. They were built in an era of constraints. Every byte mattered. Every cycle counted. Modern equivalents built in an era of abundance don't have that discipline. They work, but they're heavy. And heavy is slow even on fast machines. Wirth's law is a warning. Faster hardware doesn't automatically mean better experience. It just means more room for waste. And unless efficiency is prioritized, the waste will grow faster than the hardware can compensate. You'll keep buying faster machines to run slower software. And the treadmill keeps spinning. Gresham's law. You're hiring 2 candidates. One is excellent. Demands top salary. The other is mediocre. Cheaper. Budget is tight. You hire the mediocre one. Now you have a mediocre team member. Excellent candidates see the team and don't apply. You hire more mediocre people. Excellence leaves the market. Mediocrity becomes the standard. Bad money drives out good. That's Gresham's law. Originally about currency. When cheap currency and valuable currency circulate together, people hoard the valuable and spend the cheap. The cheap dominates circulation. The valuable disappears. The principle extends beyond money. In any system where quality and crap coexist, crap wins. The mechanism is selection pressure. If both are accepted at the same value, why offer the better one? Keep the good. Circulate the bad. This applies to products, ideas, people. If the market doesn't distinguish quality, suppliers stop providing it. Why make the better thing if the worse thing sells just as well for less effort? The worse thing takes over. Gresham's law explains content degradation. Platforms that reward engagement over quality get flooded with clickbait. Good journalism takes time and costs money. Clickbait is fast and cheap. If both get the same distribution, why make good journalism? The bad content drives out the good, not because audiences prefer it, because the system doesn't distinguish them. The law applies to labor markets. If companies don't pay for skill, skilled workers leave. Unskilled workers remain because they have fewer options. The average quality drops. Companies complain they can't find good people. They can't, because they're not paying for good people. They're paying for warm bodies. So warm bodies are what they get. Gresham's law creates race to the bottom dynamics. One company cuts quality to reduce costs. Competitors match or lose market share. Now everyone's competing on price with degraded quality. Customers accept it because it's all that's available. The good version disappears from the market entirely. Not because nobody wanted it, because the market stopped rewarding it. The law also explains platform decay. Early on, quality users join. The platform is valuable. Then it scales. Standards drop to accommodate growth. Low-quality users flood in. High-quality users leave because the environment degraded. Now the platform is dominated by low-quality content and users. It's not what anyone wanted, but it's what the incentives produced. This is why maintaining quality requires active effort. Left alone, bad drives out good. You have to create systems that distinguish quality and reward it. Otherwise, the default is degradation. The cheap, easy, low-effort option will dominate because it's cheaper and easier. And once it dominates, reversing it becomes nearly impossible. Gresham's law is a warning about what gets optimized. If you optimize for cost, you get cheapness. If you optimize for volume, you get quantity. Quality requires deliberate protection. Otherwise, the bad will drive it out. Not because the bad is better, because the bad is easier to produce. And ease wins when quality isn't enforced. Hotelling's law. Two coffee shops open on opposite ends of a street. Logical. They each serve half the customers. Then one moves closer to the center to capture more foot traffic. The other moves to compete. Eventually they're right next to each other, both fighting for the same customers, offering nearly identical products. Nobody won. The street has two shops in one spot and nothing on the ends. In competitive markets, sellers cluster toward the center instead of differentiating. That's Hotelling's law. You'd think competition drives diversity. It doesn't. It drives sameness. Because the safest strategy isn't to be different. It's to be where everyone else is. The mechanism is risk aversion. If you differentiate, you might capture a niche. Or you might get nothing. If you copy the center, you're guaranteed a share. Not the whole market, but a stable share. So everyone gravitates to the middle. The median wins. Extremes get abandoned. Hotelling's law explains why political parties drift toward the center. Elections are won in the middle. The far left and far right aren't swing voters. They're locked in. So both parties compete for moderates. Over time, platforms converge. Not because voters want the same thing, because that's where the competition is. The edges get ignored because they're not worth fighting for. The law applies beyond politics. Products, media, entertainment. If you make action movies, you aim for the broadest audience. Not the niche that loves ultra-violence or pure art films. The middle. Where the money is. So every action movie starts looking the same. Same tone, same pacing, same structure. Differentiation is risk. Convergence is safe. This creates homogenization. The market doesn't reward being different. It rewards being slightly better at being the same. So innovation dies. Everyone copies what works. Products cluster around proven formulas. Cities end up with identical chain stores. Streaming platforms license the same content. The variety shrinks to variations on a theme. Hotelling's law also explains strategic mimicry. You launch something unique. It works. Competitors don't create their own unique thing. They copy yours, but closer to the center. You're forced to move toward the center to compete. Now you're both in the middle, fighting over the same customers, and your original differentiation is gone. The market pulled you in. The law reveals a paradox. Competition should create diversity. Instead, it creates convergence, because in a competitive market, the safest move is to be near the median. Not better. Not different. Just centrally positioned. And when everyone makes that move, the center gets crowded and the edges get empty. Hotelling's law is why everything feels the same. Not because people lack creativity. Because the market punishes differentiation and rewards convergence. The middle is where the safety is. And safety beats originality every time. Zipf's law. Look at word frequency in any language. The most common word appears about twice as often as the second most common. The second appears twice as often as the third. The pattern holds all the way down. Top word half for second, half again for third. It's not planned. It's not designed. It just happens. In many datasets, the frequency of an item is inversely proportional to its rank. That's Zipf's law. First place is roughly twice second place. Second is twice third. The distribution is steep. A few items dominate. Everything else trails off into obscurity, and the pattern repeats across completely unrelated systems. The law shows up everywhere. City populations, company revenues, website traffic, income distribution. The top few capture disproportionate share, not because they're exponentially better, because winner-take-most dynamics compound small advantages into massive leads. Second place isn't close. It's half. And it drops from there. Zipf's law explains inequality. The top earner makes more than the next several combined. Not because their work is proportionally more valuable. Because small advantages compound. Slightly better network. Slightly better timing. Slightly better visibility. Each advantage builds on the last. The gap becomes a chasm. The distribution becomes a power law. The law also reveals why most things are obscure. If the top ranks dominate, the bottom ranks get almost nothing. The 100th most popular song isn't close to the 10th. It's a fraction of a fraction. Most books sell almost no copies. Most websites get almost no traffic. Most products reach almost no one. The few at the top absorb nearly all the attention. This creates long-tail dynamics. There's enormous diversity in the low ranks. Thousands of options. Millions. But their individual impact is negligible. The aggregate might matter. Any single one doesn't. So platforms focus on hits. Because serving the top 10 items reeks more people than serving the bottom 10,000. Zipf's law isn't fair. It's not designed to be. It's emergent. Preference accumulation. Network effects. Attention scarcity. All of it pushes towards steep distributions. A few winners. A massive number of also-rans. And the gap between them is structural, not accidental. The law also means disruption is rare. Dislodging the top rank requires overcoming a massive advantage. Not just being better. Being exponentially better. And even then, the new winner will likely follow the same distribution. Different names at the top. Same shape of the curve. Because the distribution isn't about the items. It's about the structure of the system. Zipf's law is a description of how things distribute. Most systems aren't flat. They're steep. A few dominate. Most fade. And the ratio between ranks is predictable. Not because of planning. Because of math. Benford's law. You check election results. Thousands of numbers. Vote totals from every precinct. And you notice something strange. Numbers starting with 1 are everywhere. Numbers starting with 9 are rare. It's not random. There's a pattern. And that pattern can catch fraud. In many naturally occurring datasets, the leading digit is more likely to be small than large. That's Benford's law. About 30% of numbers start with 1. Only 5% start with 9. It sounds backwards. You'd expect even distribution, but natural data doesn't work that way. And when it does, something's wrong. The law emerges from scale. Numbers grow logarithmically through their range. They spend more time in the lower digits. A value growing from 100 to 200 spends that entire range starting with 1. Growing from 900 to 1000, it only starts with 9 briefly before flipping to 1000. The lower digits get more coverage. The distribution tilts. Benford's law applies to surprising things: financial statements, population data, physical constants, river lengths. If the data spans multiple orders of magnitude and isn't artificially constrained, it follows the pattern. Not perfectly, but close enough to be detectable. And deviations signal manipulation. This is why auditors use Benford's law. Made-up financial numbers don't follow the distribution. People inventing data spread digits evenly. 7, 8, 9 show up too often. 1, 2, 3 not enough. The deviation is subtle, but statistical tests catch it. Fraudulent accounts stick out because the numbers look too random. The law also catches election fraud. Real vote totals follow Benford. Fabricated ones don't. If a precinct's numbers deviate significantly, it's a red flag. Not proof, but a signal worth investigating, because humans inventing numbers don't mimic natural distribution. They make them too uniform. Benford's law reveals something deeper. Randomness has structure. What looks disordered follows patterns, and those patterns expose when something isn't natural. The distribution is a fingerprint of genuine data. Break it, and you've left evidence. The law doesn't work everywhere. Constrained ranges, like test scores from 0 to 100, don't follow it. Height measurements, ages, anything bounded artificially. But for data that grows naturally across magnitudes, the pattern holds. And when it doesn't, someone likely interfered. Benford's law is a statistical truth hiding in plain sight. Most people never notice it, but it's there. In financial records, election results, scientific measurements, the first digit isn't random, it's predictable. And that predictability is a tool for auditors, for investigators, for anyone checking whether numbers tell the truth. Muphry's law. You see a typo in someone's article. You comment to correct them. 3 people immediately point out the typo in your comment. You were so focused on the mistake that you didn't notice your own. Every single time. If you criticize someone's writing, you will make a mistake in your criticism. That's Muphry's law. A deliberate misspelling of Murphy's law. The irony is the point. The act of pointing out errors creates errors. Not because you're careless, because you're focused on being right about them instead of checking yourself. The mechanism is attention tunneling. When you're correcting someone, your brain is in attack mode. Finding flaws, crafting the response. You're not proofreading yourself. You're proving them wrong. So your own writing gets sloppy. Typos slip through. Grammar fails. Word choice stumbles. And it happens right when you most want to look competent. Muphry's law is why grammar pedants constantly embarrass themselves. They post corrections confidently, then immediately get corrected. The thread becomes layers of people correcting the correctors, each one making new mistakes while fixing old ones. The original error gets forgotten in the cascade of ironic failures. The law extends beyond typos. Any criticism invites the same standard back. Complain about someone's logic and yours better be flawless. Mock someone's argument and yours better be airtight. The act of critique opens you to scrutiny, and scrutiny finds what you missed. This creates social regulation. People who constantly correct others get corrected harshly in return, not because they're wrong more often, Because they've made themselves targets, the community enforces reciprocity. You set the standard. You're held to it. Set it high through criticism. Expect no mercy when you slip. Muphry's law also reveals cognitive bias. You spot others' errors easily. Your own are invisible. When you're reading someone else's work, you're in evaluation mode. Every flaw stands out. When you're writing, you're in creation mode. Your brain autocorrects. It knows what you meant, so it doesn't see what you wrote. The mistakes are there. You just can't perceive them. The law is a reminder about humility. Everyone makes mistakes, especially when pointing out mistakes. The smarter move is gentleness. Not because being right is bad, because being smug about being right guarantees you'll be wrong about something in the process. Muphry's law doesn't mean don't correct people. It means check yourself first. Then check again, because the universe has a sense of humor, and it loves making critics look foolish. Postel's law. Your email client receives a message with broken formatting, minor protocol violation. It could reject the message as invalid. Instead, it displays it anyway, figures out what was meant, shows you the content. Meanwhile, when your client sends, it follows every rule perfectly. Clean formatting. Proper headers. No ambiguity. Generous in what it accepts. Strict in what it sends. Be conservative in what you do. Be liberal in what you accept from others. That's Postel's law. Also called the robustness principle. It's how the internet stays functional despite being built by thousands of independent implementers who all interpret standards slightly differently. Systems tolerate messiness inbound, produce correctness outbound, and that asymmetry keeps everything working. The mechanism is fault tolerance. If every system rejected anything that didn't match spec perfectly, nothing would interoperate. Email servers from different vendors. Browsers rendering different HTML. APIs talking to different clients. There's always variation. Strict enforcement would mean constant failures. Liberal acceptance means things mostly work. Postel's law is why the web doesn't break. Browsers accept malformed HTML. They guess what you meant. Fill in missing tags. Ignore invalid attributes. The page might not render perfectly, but it renders. Strict interpretation would show error messages everywhere. Liberal interpretation shows content. Users don't care about standards compliance. They care about seeing the page. The law applies beyond technology. Human interaction. Relationships. Communication. When someone says something unclear or awkward, you interpret generously. You figure out what they meant. You don't demand perfect articulation. But when you speak, you try to be clear, precise, unambiguous, generous in receiving, careful in sending. The asymmetry reduces friction. This creates robustness. Systems that apply Postel's law absorb errors. They degrade gracefully. Minor mistakes don't cascade into failures. The internet survives because servers tolerate client quirks and clients tolerate server quirks. Everyone's a little sloppy. Everyone's a little forgiving. The system functions. But the law has costs. Liberal acceptance enables bad implementations. If broken behavior is tolerated, why fix it? Sloppy code persists because it works well enough. Standards decay because strict compliance isn't required. Over time, the spec becomes meaningless. Everything works, but nothing quite matches what was intended. Postel's law also creates security risks. Accepting liberal input means accepting malicious input disguised as mistakes. Tolerating protocol violations means tolerating exploits. The generosity that keeps systems working also opens attack surfaces. Robustness and security trade-off. You can't have both completely. The law is a philosophy, not just for systems. For life, give others slack. Hold yourself to standards. Accept that people will be imperfect. Don't demand perfection from them. Demand it from yourself. The asymmetry isn't weakness. It's what makes cooperation possible. Because if everyone demanded perfect compliance from everyone else, nothing would ever work. Kidlin's law. You're stuck on a problem. It feels overwhelming, massive, impossible. You can't even think about it without anxiety spiking. Then you sit down and write it out. What exactly is the problem? What are the constraints? What's actually wrong? Halfway through writing, the answer appears. You didn't solve it yet, but you can see how to. If you write down the problem clearly, you're halfway to the solution. That's Kidlin's law. Not because writing is magic, because fuzzy problems stay unsolvable. Clear problems reveal their own answers. The act of articulation is half the work. The mechanism is forced clarity. When a problem lives in your head, it's shapeless, big, vague, scary. Writing demands specificity. What exactly is wrong? Not everything. What specifically? That question starts breaking the mass into pieces. And pieces are manageable where masses aren't. Kidlin's law explains why talking through problems helps. You explain it to someone. Halfway through, you solve it yourself. They didn't do anything. The act of externalizing forced you to structure the mess. Verbalization requires clarity. Clarity reveals solutions. The other person was just a rubber duck. The solution came from articulating, not from their input. The law works because most problems aren't actually complex. They're just poorly defined. You don't know what you're solving. So you can't solve it. The moment you write out exactly what's wrong, the path forward usually becomes obvious. Not easy, but visible. And visible is solvable. This is why good problem statements are half the battle. Engineering. Business. Relationships. If you can state the problem clearly, you can probably fix it. If you can't state it clearly, you'll flail. The work isn't finding the solution. It's clarifying what needs solving. Get that right and solutions follow. Kidlin's law also reveals why vague complaints persist. This project is a mess. Okay, what specifically is wrong? Everything. Nothing gets fixed. Because the problem isn't defined. It's just a feeling of wrongness. Write down what's actually broken. Concrete specifics. Now you have something to address. And addressing it might be straightforward once it's clear. The law applies to personal problems too. You're anxious. About what? Write it down. Not everything. What specifically? Often writing reveals the anxiety is focused on one or two concrete things. And those things might have concrete solutions. Or they might not. But either way, they're smaller than the vague dread that filled your head before you articulated them. Kidlin's law isn't about writing skills. It's about thinking clearly. And writing forces clear thinking. You can't write vaguely without noticing. The words demand precision. So imprecise thoughts get refined, and refined thoughts reveal paths forward. The problem doesn't get easier. It gets clearer. And clear problems are halfway solved. Law of Unintended Consequences. Prohibition seemed logical. Ban alcohol, eliminate the social problems it causes. Crime drops. Public health improves. Society benefits. Instead, crime exploded. Organized gangs took over distribution. People drank more dangerous homemade alcohol. Corruption spread through law enforcement. The ban created exactly what it was supposed to prevent. Worse problems. Different problems. Problems nobody predicted. Actions have effects beyond the intended outcome. Often, those unintended effects dominate. That's the law of unintended consequences. You solve one problem and create 3 new ones. Not because the solution was wrong. Because systems are interconnected. Change one part, ripple effects spread everywhere, and those ripples don't follow your plan. The mechanism is complexity. Systems of feedback loops. Hidden dependencies. Second-order effects. You can't predict them all. So you act on the obvious direct connection. Ban alcohol, drinking stops. Except people want alcohol. So black markets form. Markets need enforcement. Enforcement creates violence. Violence corrupts institutions. The cascade wasn't planned. It was inevitable once the system adjusted. The law shows up constantly. Antibiotics cure infections. Overuse creates resistant bacteria. Now infections are harder to treat. Fuel efficiency standards make cars lighter. Lighter cars are less safe in crashes. More efficiency, more deaths. Mandatory minimum sentences reduce judicial discretion. Now prisons overflow with non-violent offenders and real criminals that get less attention because resources are stretched. Unintended consequences aren't always bad. Viagra was developed for heart conditions. Turned out it had a different, more profitable effect. The internet was built for military communication. Became the foundation of modern commerce and culture. Post-it notes were failed glue. Penicillin was accidental mold. Sometimes the unintended outcome is better than the intended one. But usually unintended consequences are problems, because systems resist change. Impose a new rule, the system adapts around it, often in ways that undermine the rule's purpose. Rent control keeps prices low. Landlords stop maintaining buildings. Supply drops. Prices rise for uncontrolled units. The people you want it to help can't find housing. The system routed around your intervention. The law doesn't mean don't act. It means think through second-order effects. What happens after the obvious thing happens? Who adapts? How do they adapt? What new equilibrium forms? Most interventions fail not because the logic was wrong, because the logic stopped at the first step. The system has 20 more steps, and those steps don't care about your intentions. Unintended consequences are the tax on intervention. Every action pays it. You can't avoid them. You can only try to predict them. And even then, you'll miss most of them, because the system is smarter than you. It's had longer to optimize, and it will find paths you didn't know existed. Law of Diminishing Returns. First hour studying, you learn a lot. Concepts click. Material sticks. Second hour, still productive but slower. Third hour, you're reading the same page. Fourth hour, nothing's going in. You're putting in more time. Getting less out. The effort increases. The benefit doesn't. Past a certain point, additional input yields progressively smaller output. That's the law of diminishing returns. Early investment pays off. Later investment pays less. Keep pushing, and eventually you're working harder for almost nothing. The curve flattens. Then it inverts. The mechanism is saturation. The easiest gains come first. Low-hanging fruit. Quick wins. Then you're working on harder problems with less obvious solutions. The same effort that produced big gains early produces tiny gains later. Not because the effort is worse, because the easy opportunities are exhausted. Diminishing returns explains why everything plateaus. Fitness, learning, marketing. The first few weeks at the gym, dramatic improvement. After a year, progress is measured in fractions. The first ad campaign, huge reach. The fifth, marginal gains. Early employees transform the company. Later hires barely move the needle. The pattern is universal. Early advantage, later plateau. Eventually decline. The law creates optimization problems. Keep investing past the point of diminishing returns and you're wasting resources. But where's the point? You don't know until you pass it. So people overshoot. They keep pushing because it worked before. By the time diminishing returns are obvious, they've already spent too much. This is why specialists exist. If every additional hour of study yields less, why study broadly? Go deep in one area. Master it. The curve might flatten, but you're still ahead of generalists who spread time across many areas and hit diminishing returns everywhere. Specialization is an answer to diminishing returns. Concentrate effort where the curve still climbs. The law also explains why scaling is hard. Double your ad spend, you don't double sales. You've already reached the responsive customers. The next segment is harder to convert. Double your team, you don't double output. Communication overhead eats the gains. Diminishing returns kick in everywhere. Growth doesn't scale linearly. It scales logarithmically. Then it stops. You can't escape diminishing returns. You can only manage them. Recognize when you've hit the plateau. Stop adding more of the same. Shift to something else. The early gains are gone. Chasing them wastes effort. Find a new curve. Start climbing again. Because the only way to beat diminishing returns on one thing is to start something new where the returns aren't diminished yet. Law of Triviality. The committee meets to approve a nuclear power plant. $1 billion project. Complex engineering. Safety systems. Environmental impact. Discussion takes 15 minutes. Everyone nods. Approved. Next item. The bike shed outside the office. $20 paint job. The debate goes for an hour. Everyone has an opinion. Colors are compared. Costs are questioned. The trivial decision consumes more time than the critical one. Organizations give disproportionate weight to trivial issues because they're easier to understand. That's the law of triviality, also called bike shedding. Complex decisions get rushed. Simple ones get endless debate. Not because simple things matter more, because everyone feels qualified to have an opinion on them. The mechanism is comprehension. The nuclear plant is too complex. Most committee members don't understand it. So they defer to experts. The bike shed is simple. Everyone understands paint. So everyone engages. The accessible topic gets attention. The important but difficult topic gets rubber stamped. Complexity intimidates. Simplicity invites participation. The law explains meeting dysfunction. Major strategic decisions pass quickly. Minor details spark arguments. The product roadmap gets approved in 20 minutes. The office seating arrangement takes 2 hours. The important thing is complicated. People don't want to look stupid, so they stay quiet. The trivial thing is easy. People can participate, so they do. Ludley. Triviality bias creates misallocated attention. The things that matter get insufficient scrutiny. The things that don't matter get too much. Not because people are stupid. Because engagement follows comprehension, not importance. If you can understand it, you'll debate it. If you can't, you won't. So the trivial consumes the calendar. This is why experts struggle in organizations. They know the complex thing matters, but they can't get anyone to focus on it. Meanwhile, people who don't understand the complex thing dominate discussions about trivia. And because trivia is accessible, it feels productive. Everyone contributed. Everyone had a voice. Nothing important got decided. The law compounds with organizational size. Bigger groups mean more people who don't understand the complex issue. So more people default to debating trivia. The bike shed discussion becomes a full-day workshop. The nuclear plant gets 3 slides in a deck nobody reads. Importance inverts with accessibility. Triviality bias is structural. You can't fix it by telling people to focus on what matters. Because what matters isn't accessible to them. The only fix is decision design. Limit who weighs in on complex decisions. Restrict debate time on simple ones. Force proportionality. Otherwise, the trivial will dominate. Not because it should, because it can. Law of the instrument. You learned SQL. You're good at it. Every problem you encounter, you think in terms of databases. Relationships. Queries. Tables. Someone mentions a data problem. You propose a relational database. They mention user tracking. Another database. Content management. Database. Eventually, someone points out that not everything needs a database. You were so focused on your tool that you stopped seeing other options. If the only tool you have is a hammer, everything looks like a nail. That's the law of the instrument. Master one approach and you apply it everywhere. Not because it's always appropriate, because it's what you know. Competence creates blindness. You see problems through the lens of your solution, and that lens distorts. The mechanism is cognitive efficiency. Learning new tools is hard. Using familiar tools is easy, so you default to what you know. A programmer uses code to solve problems that don't need code. A lawyer frames issues as legal questions when they're not. A designer adds visual solutions to problems that need process fixes. The tool becomes the answer before the question is fully understood. The law explains professional bias. Ask a surgeon how to treat a condition, they'll suggest surgery. Ask a therapist, they'll suggest therapy. Not because they're dishonest, because they see the world through their expertise. Their tool is surgery or therapy. So that's what they reach for. Other approaches don't exist in their framework. The instrument defines the problem space. This creates solution myopia. Organizations hire specialists. Specialists apply their specialty, whether it fits or not. Marketing teams see marketing problems. Engineering teams see technical problems. Finance sees budget issues. Everyone's solving the problem they're equipped to solve, not necessarily the problem that exists. The instrument shapes perception. The law also drives technology adoption. A company invests in a platform. Now every project uses that platform. Not because it's the best fit, because it's already there. The sunk cost becomes the default tool, and once it's the default, everything gets framed to fit it. The instrument justifies itself by being available. Breaking the law requires deliberate discomfort. Force yourself to consider tools you don't know. Ask what someone with a different background would do. Recognize when you're reaching for the hammer out of habit, not necessity. The tool you're comfortable with isn't always the tool the problem needs. The law isn't about avoiding specialization. It's about recognizing its limits. Expertise is valuable, but expertise narrows vision. The better you get with one tool, the more you'll see problems that tool can solve, and the less you'll see problems it can't. Everything starts looking like a nail. Not because it is, because that's all a hammer knows. Pareto Principle. 20% of your customers generate 80% of your revenue. 20% of your bugs cause 80% of crashes. 20% of your features get 80% of usage. The ratio isn't exact, but the pattern holds. Most of the results come from a minority of the causes. A small slice delivers disproportionate impact. Roughly 80% of effects come from 20% of causes. That's the Pareto Principle, also called the 80-20 rule. It's not a law of physics, it's an observed distribution. And it shows up everywhere. Effort isn't linear, results cluster. A few inputs dominate outcomes. Most inputs barely matter. The mechanism is inequality. Not all causes are equal. Some are vastly more impactful than others. The most important customer is worth more than dozens of marginal ones. The worst bug affects more users than hundreds of minor annoyances. So outcomes concentrate. The top slice captures most of the value. The rest splits what's left. The Pareto Principle explains where to focus. If 20% of your work drives 80% of results, focus on that 20%. Ignore the rest. Sounds ruthless. It's efficient. Most effort is wasted on low-impact activity. Identifying the high-impact minority and concentrating there multiplies effectiveness. This is why prioritization matters. Without it, effort spreads evenly. You spend equal time on everything, but everything isn't equal. Some tasks are 10 times more valuable than others. The Pareto Principle says find them. Do those. Let the others slide. The 80% of low-impact work can wait. Or disappear. You'll barely notice. The principle also reveals why perfectionism fails. You can spend 80% of your time getting the last 20% of quality. But that final polish often adds minimal value. The first 80% of quality came from 20% of effort. The last 20% of quality takes 80% of effort. Diminishing returns. The Pareto Principle and the Law of Diminishing Returns intersect. Most value comes early. Finishing costs too much for too little. The principle isn't just about work. It's about everything. 20% of your wardrobe gets 80% of wear. 20% of your contacts provide 80% of your opportunities. 20% of your worries cause 80% of your stress. Most things don't matter much. A few matter enormously. Identify the few. Optimize there. The danger is misidentifying the 20%. Spend your time on the wrong things, thinking they're high impact, and you've wasted effort on the 80%. The principle only helps if you correctly identify what matters. And what matters isn't always obvious. It requires analysis, measurement, honesty about what actually drives results versus what feels important. The Pareto Principle is a focusing tool. Most of what you do doesn't matter. A small fraction does. Find that fraction. Do it well. Everything else is distraction. Harsh but true. 80-20 isn't fair. It's just how results distribute. And once you see it, you can't unsee it. Most effort is wasted. Most value comes from the minority. Optimize accordingly. Boyle's Law of Teams. 3 people working on a project. Everyone contributes. Ideas flow. Decisions happen quickly. Someone suggests adding more people to go faster. The team doubles to 6. Now meetings take longer. Coordination overhead increases. Individual output drops. Each person contributes less because there are more people to coordinate with. You added capacity. Productivity per person fell. As team size increases, individual contribution decreases. That's Boyle's Law of Teams, named after the idea that pressure and volume are inversely related. More people means less output per person. Not linearly. Disproportionately. The team gets bigger. Each member does less. Total output might increase slightly, but efficiency collapses. The mechanism is coordination cost. Every person added creates new communication channels. A team of 3 has 3 channels. A team of 6 has 15. Double the people, you quintuple the coordination burden. Meetings multiply. Alignment takes longer. Decisions require more consensus. The work that needs doing doesn't scale with team size. The overhead does. Boyle's law explains why small teams outperform large ones. 2 pizza teams, the idea that if you can't feed a team with 2 pizzas, it's too big. Small teams move fast. Everyone knows what everyone else is doing. Decisions are quick. Large teams move slowly. Coordination dominates. Individual contribution shrinks because most time goes to managing interfaces between people instead of doing work. The law creates a productivity paradox. You need more output, so you add people. Output goes up slightly, but efficiency tanks. Each person is less productive because they're spending time coordinating instead of creating. Total work done increases. Work per person decreases. At some point, adding people makes the team slower, not faster. You've crossed the threshold where coordination cost exceeds added capacity. This is why scaling teams is hard. You can't just keep adding people. Past a certain size, each addition reduces effectiveness. The team becomes a coordination machine instead of a production machine. Meetings. Status updates. Alignment. The work becomes managing the work. Actual output stagnates. Boyle's law also explains why splitting teams works. Break a 10-person team into 2 5-person teams. Each smaller team is more efficient, less coordination overhead. Faster decisions. More individual ownership. The total output of 2 small teams often exceeds 1 large team. Not because you added people, because you reduced coordination burden. The law doesn't say teams should be tiny. It says there's a size threshold. Below it, adding people helps. Above it, adding people hurts. And that threshold is lower than most organizations think. 3 to 7 people is often optimal. Beyond that, returns diminish fast. Beyond 10, you're not adding productivity, you're adding bureaucracy. Boyle's law is a warning. More people isn't always better. Often, it's worse. Bigger teams feel productive, more meetings. More activity. But activity isn't output, and when coordination consumes capacity, you're just spinning faster while moving slower. Small teams ship. Large teams coordinate. And coordination doesn't deliver products. Beckstrom's law. How much is the internet worth to you? Metcalfe's law says look at how many users there are. More users, more value. But that's the network's total value. Beckstrom's law asks a different question. What's it worth to you specifically? What would you pay to keep your access? The answer isn't the same for everyone, and the sum of everyone's individual answers is the network's real value. The value of a network equals the sum of what each user gains from it. That's Beckstrom's law. It's not about total connections. It's about individual benefit. Some people would pay thousands to keep internet access. Others barely care. The network's value isn't an abstract number. It's the aggregate of what each person would lose if it disappeared. The mechanism is heterogeneous utility. Not everyone uses the network the same way. A business depends on email and cloud services. A student uses it for research and entertainment. A retiree checks news and talks to family. Each person extracts different value, so the network's worth varies wildly by user. The total is the sum of those varying individual values. Beckstrom's law explains why some networks succeed and others don't. It's not just about size. It's about how much value users actually get. A small network where everyone gains enormous value is more robust than a massive network where most users are indifferent. Size matters, but retained value matters more. Those users who didn't care, the network barely notices. Those users who depended on it, and suddenly there's a problem. The law also reveals pricing challenges. Charge everyone the same, and you're undercharging heavy users and overcharging light ones. Heavy users get a bargain. Light users leave. What's left is a concentrated base of high-value users. That's fine if they sustain the network. But if the network needed scale, pricing just killed it. The value distribution is uneven. Flat pricing doesn't capture that. This is why freemium works. Most users get minimal value. Free tier. A few users get massive value. They pay. The pricing matches the value distribution. The network captures revenue from those who benefit most without losing those who benefit least. Beckstrom's law in action. Price to the value gradient, not to the average. The law contrasts with Metcalfe. Metcalfe says value grows with connections. Beckstrom says value grows with extracted benefit. Both can be true, but they point to different strategies. Metcalfe optimizes for growth. More users, more value. Beckstrom optimizes for utility. Better experience, more value per user. Networks need both. But if you only focus on growth, you might build a massive network nobody actually cares about. Beckstrom's law is a reminder. The network isn't valuable because it's big. It's valuable because people find it useful, and usefulness is individual. Aggregate the individual gains. That's the network's worth. Ignore individual value, and you're measuring the wrong thing. Linus's law. You're debugging code, staring at it for hours. Can't find the problem. Then you show it to someone else. Within minutes, they spot it. Not because they're smarter, because they're seeing it fresh. One person, one perspective, limited visibility. More people, more perspectives. Bugs that hide from you stand out to someone else. Given enough eyes, all bugs are shallow. That's Linus's law, named after Linus Torvalds of Linux. The principle is simple. No bug survives widespread scrutiny. Someone will find it. Not because any individual is brilliant, Because enough people looking means every corner gets examined. The crowd catches what individuals miss. The mechanism is parallel inspection. One person checks the code sequentially. Limited time. Limited focus. 100 people check it in parallel. Different backgrounds. Different assumptions. Different mental models. What one person overlooks, another notices. Bugs aren't uniformly hard to find. They're hard for specific people with specific blind spots. Diversify the inspectors, and someone won't have that blind spot. Linus's law explains why open source works. Proprietary code gets reviewed by a small team. Same company. Same training. Same biases. Open source gets reviewed by anyone interested. Different companies. Different contexts. Different motivations. The bug that the original team missed gets caught by someone in a completely different use case. The diversity of inspection is the strength. The law applies beyond code. Wikipedia works the same way. Any individual article might have errors. But thousands of readers means someone notices. They fix it. The next error gets caught by someone else. Over time, the article converges toward accuracy. Not because any one editor is authoritative. Because enough people checking means errors don't survive long. Crowdsourced fact-checking follows Linus's law. One fact-checker has limits. Bias. Blind spots. Time constraints. 1,000 fact-checkers in parallel cover more ground. Different expertise. Different sources. Different scrutiny angles. The false claim that slips past one gets flagged by another. The law doesn't require experts. It requires volume and diversity. But Linus's law has conditions. It only works if people are actually looking. 1 million potential reviewers who don't review accomplish nothing. The law needs active engagement. Open source projects with no contributors don't benefit from distributed review. They're just public, not reviewed. Eyes need to be watching and motivated to report what they find. The law also assumes someone acts on findings. Bugs found but not fixed stay bugs. Reports ignored don't improve quality. Linus's law describes discovery, not resolution. The eyes find the problem. Then someone has to care enough to fix it. Without that step, you've just documented failure instead of preventing it. Linus's law is an argument for transparency. Hide the work, and only a few people can check it. Expose it, and the crowd finds the flaws. More reviewers means fewer surviving errors. Not because crowds are smart, because crowds are diverse, and diversity of perspective catches what uniformity misses. Segal's law. You step on one scale. It says 180. You trust it. Simple. Then you step on another scale. It says 175. Now you don't know your weight. Is the first scale 5 pounds high? Is the second 5 pounds low? Are they both wrong? You had certainty with one measurement. 2 measurements gave you doubt. A person with one watch knows what time it is. A person with 2 watches is never sure. That's Segal's law. One source of information provides confidence. Multiple conflicting sources create confusion, not clarity. The additional data doesn't help. It undermines trust. You thought you knew. No, you don't. The mechanism is conflicting authority. One source speaks with certainty. You accept it. 2 sources disagree. Now you need a T-breaker, but you don't have one. So you're stuck evaluating which source is more reliable. That evaluation is harder than the original question. You wanted to know the time. Now you're auditing timepieces. The added information made the problem worse. Segal's law explains decision paralysis. Ask one expert, they give advice. You follow it. Ask 3 experts, they contradict each other. Now you can't decide. The additional expertise didn't clarify. It muddied. You're not more informed. You're more confused. One voice is actionable. Multiple voices require synthesis you're not equipped to do. The law shows up in data. One metric tells a story. The product is growing. Then you add another metric. It says the opposite. Engagement is up, but retention is down. Revenue is rising, but profit is falling. Now you don't know if things are good or bad. The single metric gave direction. Multiple metrics gave conflict. And resolving that conflict requires understanding you don't have. This is why organizations struggle with dashboards. 20 metrics, some green, some red. What's the conclusion? Nobody knows. One clear metric, even if imperfect, drives action. 20 conflicting metrics drive meetings. The data became the problem instead of the solution. Siegel's law at scale. Too much information, not enough clarity. The law also reveals trust dynamics. People trust singular authoritative sources. The doctor says this. The manual says that. They believe it. Then another doctor says something different. Trust collapses. Not in one doctor. In doctors generally. The conflict suggests both might be wrong. Or that the field doesn't know. Either way, confidence drops. One source preserves trust. Two conflicting sources destroy it. Siegel's law doesn't mean ignore multiple data points. It means conflicting information without resolution is worse than incomplete information with confidence. If you can reconcile the conflicts, multiple sources help. If you can't, they just create doubt. And doubt freezes action. The law is a warning about information overload. More isn't always better. Sometimes more is just noise. One clear signal beats 3 mixed ones. Know the time, or spend your life wondering which clock is right. Pick one. Move forward. Because certainty, even if slightly wrong, beats paralysis from conflicting truths. Betteridge's law. You're scrolling through news. Headline reads, "Is this the breakthrough that cures cancer?" You click. The article is speculative. Tentative. Mostly hedging. The answer to the headline question is no. Next headline. Could this change everything? Again, no. Will AI replace your job? Probably not, according to the article itself. The question format isn't inquiry. It's bait. Any headline that ends in a question mark can be answered no. That's Betteridge's law of headlines. If the answer were yes, the headline would be a statement. New breakthrough cures cancer. But it's not yes. So it's a question. The question format signals uncertainty disguised as curiosity. The answer is almost always no. Or at least, not really. The mechanism is journalistic hedging. Writers want engagement. Questions engage. But they can't state false claims. That's liable. So they ask questions. Is X happening? Shields them from accountability. If X isn't happening, they didn't lie. They just asked. The question mark is legal cover wrapped in clickbait. Betteridge's law explains headline skepticism. Declarative headlines carry commitment. The writer is stating a fact. Question headlines carry none. The writer is implying possibility without asserting truth. It's a signal. If the claim were solid, it wouldn't be phrased as a question. The question reveals doubt. And if the writer doubts it, you should too. The law applies beyond news. Marketing uses the same trick. Could this product change your life? Probably not, or they'd say it does. Is this the best deal ever? No, or the headline would claim it outright. The question format creates intrigue without making promises. It's suggestive without being accountable. And that's a red flag. Betteridge's law also appears in social media. Posts framed as questions. Is anyone else tired of this? Yes, but that's not the point. The question is engagement farming. It invites responses. Declarative statements don't. So everything becomes a question. Even when the poster already has an opinion. The question format is manipulation, not inquiry. The law doesn't apply to all questions. Genuine open questions exist. How does this work? Is asking for explanation. What happened next? Is narrative structure. Those aren't Betteridge violations. The law targets questions that imply a controversial answer without committing to it. Speculative questions. Leading questions. Questions that suggest rather than ask. The law is a heuristic. See a headline question, assume the answer is no. You'll be right most of the time. Not always. But often enough that the pattern is reliable. Question headlines are weak claims in disguise. If the claim was strong, it wouldn't be hiding behind a question mark. Betteridge's law trains skepticism. Questions in headlines aren't innocent. They're signals of uncertainty or manipulation. The writer doesn't believe it enough to state it. So neither should you. Read past the question. Find the answer. It's usually no. Or nothing. Because if it were yes or something, the headline would have said so. Fitz's law. You're using a website. The submit button is huge and centered. Easy to hit. The cancel button is tiny and tucked in the corner. Takes effort to find and click. That's intentional. The designer wants you to submit, so they made it easy. They don't want you to cancel, so they made it hard. The size and distance of a target determines how quickly you can reach it. The time to reach a target is a function of distance and size. That's Fitz's law. Closer and bigger means faster. Farther and smaller means slower. It's not just about physical space. It's about effort. Making something easy to hit makes it more likely to be hit. Making it hard reduces the chance. Every interface decision about placement and size is shaping behavior. The mechanism is motor control. Moving a cursor or a finger to a target requires precision. Large targets need less precision. Small targets need more. Close targets require less movement. Distant targets require more. Time increases with distance. Time increases with required accuracy. Combine far and small, and you've maximized difficulty. Combine close and large, and you've minimized it. Fitz's law explains interface design. Buttons you want users to click should be big and close to where their attention is. Buttons you want them to avoid should be small and far. Delete buttons are tiny and require confirmation. Submit buttons are prominent and easy. The design encodes priority through physics. Important actions are effortless. Dangerous or undesired actions are friction-laden. The law applies to physical spaces too. Emergency exits are large and clearly marked. You need to reach them fast under stress. Less critical doors are smaller and unmarked. The urgency is encoded in size and placement. Fitz's law isn't just digital. It's any environment where humans need to reach targets. Make it big and close if it matters. Make it small and far if it doesn't. This is why Menace put frequent actions at the top. Less scrolling, less movement, faster access. Rare actions go to submenace. More distance, more time. The structure maps to usage frequency. What people use most should be easiest to reach. What they use rarely can be buried. Fitz's law prioritizes by effort. The law also reveals dark patterns. Unsubscribe links buried in tiny text at the bottom of long emails. Cancel buttons hidden behind multiple clicks. The friction is intentional. The designer is using Fitz's law against you. They've maximized distance and minimized size to reduce the chance you'll follow through. It works. Most people give up. The effort barrier is the point. Fitz's law is a tool. Use it to help users by making important actions easy. Or use it to manipulate users by making unwanted actions hard. Either way, the physics doesn't change. Distance and size determine effort. And effort determines behavior. Design the interface. Shape the outcome. Miller's Law. You're at a restaurant. The waiter lists 8 daily specials. By the time they finish, you've forgotten the first 3. You ask them to repeat. They do. They do. You forget again. It's not that you're not paying attention. It's that 8 items is too many to hold in your head at once. Your brain has limits. And 8 exceeds them. The average person can hold about 7 items in working memory. That's Miller's Law. 7 plus or minus 2. Some people manage 9. Some only 5. but the range clusters around 7. Try to remember more and items start dropping out. Your brain isn't built to juggle 10 things simultaneously. It's built for around 7. Push past that and retention collapses. The mechanism is cognitive load. Working memory is limited capacity. It's not storage. It's active processing space. The mental equivalent of RAM, not a hard drive. You can hold 7 things while you think about them. More than that, and you need to write them down or chunk them into groups. Otherwise, they disappear. Miller's law explains interface design. Menace with 10 options overwhelm. Menace with 5 don't. Phone numbers are broken into chunks. 3 digits, 4 digits. Not 10 digits in a row. The chunking keeps each segment under the magic number. You remember the chunks, not the individual digits. That's how you exceed the limit. By organizing within it. The law shows up in presentations. A slide with 12 bullet points loses the audience. They can't hold that much. By point 8, they've forgotten point 2. A slide with 5 points works. You can track them. The message lands. More information doesn't mean more retention. It means more forgetting. Miller's law sets the ceiling. Exceed it at your own risk. This is why lists have limits. Grocery lists longer than 7 items need to be written. To-do lists over 7 tasks feel overwhelming. The brain can't keep them all active. So it drops some, or gets paralyzed trying to hold them all. The limit isn't about intelligence. It's about architecture. Working memory has a fixed capacity. Use it or lose it. Miller's law also applies to decision-making. Offer someone 3 choices, they'll evaluate them. Offer 15 and they'll freeze. Too many options exceed working memory. You can't hold all the variables in your head at once. So you either pick randomly, give up, or suffer decision fatigue. The paradox of choice isn't about wanting less. It's about cognitive limits. More options than you can process isn't freedom. It's overload. Breaking through the limit requires chunking. Group items into categories. 7 categories, 7 items each, gives you access to far more than 7 total items. But you're never holding more than 7 in active memory at once. The categories act as containers. You navigate between them. Inside each, the limit still applies. But the structure lets you scale beyond it. Miller's law is a constraint. 7 items, that's the workspace. Design for it. Present information in digestible chunks. Keep lists short. Limit options. Respect the ceiling. Because your audience isn't ignoring you. Their working memory is full, and full means nothing else fits. Yerkes-Dodson Law. Low stakes, low effort. You're barely trying. Performance suffers because you don't care enough. Raise the stakes. Add pressure. Performance improves. You focus. You try harder. Keep raising the stakes. At some point, performance peaks. Then it starts dropping. More pressure doesn't help anymore. It hurts. Too much stress, and you choke. The curve isn't linear. It's an arc. And past the peak, more motivation makes things worse. Performance increases with stress up to a point, then declines. That's the Yerkes-Dodson Law. Some pressure helps. Too much destroys. The relationship is a curve. Low arousal, low performance. Moderate arousal, peak performance. High arousal, performance collapses. The sweet spot is in the middle. Miss it on either side, and you underperform. The mechanism is cognitive resource allocation. Low stress means low engagement. Your brain isn't fully activated. You're coasting. Moderate stress focuses attention, sharpens processing, mobilizes energy. But high stress floods the system. Anxiety consumes working memory. Panic narrows focus to threats instead of tasks. The resources that should go to performance get redirected to managing fear. You're trying harder but thinking worse. The Yerkes-Dodson Law explains why some people thrive under pressure and others crumble. It's not about toughness. It's about where you are on the curve. The person who thrives is at moderate arousal. The pressure pushed them to the peak. The person who crumbles is past it. More pressure pushed them over. Same external stress. Different positions on the curve. Different outcomes. The law also explains why difficult tasks need less pressure than easy ones. Easy tasks tolerate high arousal. You can be stressed and still execute. The task doesn't demand much cognitive capacity. Hard tasks require precision, complex thinking, low arousal. Too much stress, and you can't hold the complexity in your head. The sweet spot for hard tasks is lower than for easy ones. What feels like motivating pressure for simple work is paralyzing for complex work. This is why cramming fails. High-stakes exam, maximum stress. You're past the peak, working harder but retaining less. The pressure that should motivate is sabotaging comprehension. Lower the stakes, paradoxically, and performance improves. Not because you care less, because you're back at optimal arousal. The curve bent back down. You needed less pressure, not more. The Yerkes-Dodson Law creates a management problem. Leaders assume more pressure equals more output. It doesn't. It equals more output up to a point. Past that, it equals worse output. But leaders can't see the curve. They just see effort. And effort looks productive even when it's not. So they keep adding pressure. Deadlines tighten. Expectations rise. And performance degrades while everyone works harder. The law is a reminder. Stress is a tool, not a solution. Use enough to engage. Not so much that it overwhelms. The peak is real, and it's lower than most people think, especially for work that actually matters. Ashby's Law. You're managing a simple system, a lemonade stand, one product, one location, basic decisions. You handle it easily. Now you're managing a restaurant, multiple dishes, suppliers, staff schedules, regulations, kitchen equipment. The decisions multiply, the variables interact. You can't track it all. Your simple management approach doesn't work anymore. The system outgrew your ability to control it. A system can only be controlled by something at least as complex as itself. That's Ashby's law of requisite variety. Simple problems need simple solutions. Complex problems need complex solutions. You can't control chaos with simplicity. The controller must match the system's complexity. Anything less, and parts of the system slip out of control. The mechanism is state matching. A system has many possible states. The controller needs responses for each state. If the controller has fewer responses than the system has states, some states go unhandled. The system does something. The controller has no answer. Control fails. Only when the controller's variety matches or exceeds the system's variety can full control exist. Ashby's law explains why simple rules fail in complex environments. Just work harder doesn't manage organizational dysfunction. The dysfunction has dozens of causes. One response can't address them all. Simple slogans, broad mandates, universal policies. They collapse under real-world complexity because they lack the variety to match the problem's variety. The system outruns the solution. The law shows up in regulation. Simple rules for complex industries don't work. Financial markets, healthcare, technology, each has enormous variety, thousands of edge cases, constantly evolving. A 10-page regulation can't control it. The system has more states than the regulation has responses. So it routes around, finds gaps, exploits ambiguities. Not because people are malicious, because complexity exceeds control capacity. This is why micromanagement fails at scale. A manager trying to control every decision in a large organization doesn't have the bandwidth. Too many states, too many variables. They can't process them all. So they oversimplify. Force everything into a few categories they can manage. But the organization's real complexity doesn't fit. Decisions get bad. The mismatch between system variety and managerial variety creates dysfunction. Ashby's law also reveals why decentralization works. You can't centrally control a complex system. Central control lacks variety. But distribute control. Let local managers handle local complexity. Now the total control variety increases. Each manager handles their subset. Aggregate them, and you match the system's total variety. The organization becomes controllable not through central command, but through distributed response. The law doesn't mean every problem needs a complicated solution. It means the solution's complexity must match the problem's complexity. Sometimes that's simple. Sometimes it's not. But pretending complex problems have simple solutions just means the problem wins. The system will always defeat a controller with insufficient variety. Always. The math doesn't allow otherwise. Godwin's law. You're in an online debate. Politics. Technology. Anything controversial. At first, it's civil. Arguments. Counter-arguments. Evidence. Then someone gets frustrated. They reach for the ultimate comparison. This is just like what the Nazis did. And the conversation dies. Because once Hitler enters the chat, productive discussion is over. Everyone's now arguing about whether the comparison is valid instead of the original topic. As an online discussion grows longer, the probability of a comparison involving Nazis or Hitler approaches certainty. That's Godwin's law. It's not about being right or wrong. It's about inevitability. Long enough thread, someone will make the comparison. It's a pattern. A social law of internet dynamics. And it usually signals the end of useful conversation. The mechanism is escalation. Debates intensify. People want stronger arguments. Analogies get more extreme. And in Western discourse, Nazi comparisons are the rhetorical nuclear option. The ultimate evil. So when someone wants maximum impact, that's where they go. Not because it's accurate. Because it's final. The discussion can't escalate past Hitler. There's nowhere left to go. Godwin's law explains conversation death. The Nazi comparison is so extreme it derails everything. Suddenly, the debate isn't about the original topic. It's about whether the comparison is appropriate. People defend against the analogy instead of engaging the point. Or they're so offended they disengage entirely. Either way, the substantive discussion ends. The comparison killed it. The law also reveals argument weakness. Resorting to Nazi comparisons usually signals a failing position. You've run out of relevant arguments. So you reach for shock value. It's a Hail Mary. And it rarely works. Because everyone recognizes it as rhetorical desperation. The comparison doesn't strengthen the point. It undermines it. By suggesting you have nothing better. Godwin's law applies beyond Nazis. Any extreme comparison does the same thing, comparing minor inconveniences to slavery, comparing policy disagreements to genocide, comparing regulations to tyranny. The pattern holds. Extreme analogies don't persuade. They terminate. Because the gap between the comparison and the reality is so vast that it becomes the focal point. The original issue disappears. This is why good arguments avoid extreme comparisons. Not because they're always wrong. Sometimes authoritarian patterns do echo historical atrocities. But the comparison is so inflammatory that it destroys the discussion. Even when apt, it shifts focus from substance to analogy. And that shift rarely helps. The rhetorical impact overwhelms the logical content. Godwin's law is a warning. Watch for the Hitler comparison. When it appears, the conversation is probably over. Not because Hitler mentions are forbidden. Because they signal escalation past productive exchange. The debate has left reason and entered spectacle. And spectacle doesn't resolve disagreement. It just makes it louder. Parkinson's law of delay. The project proposal sits on someone's desk, waiting. You ask for a decision. We're still reviewing it. Weeks pass. You follow up. We'll get back to you soon. Months go by. The answer never comes. But the absence of an answer is an answer. They're not saying yes. They're not saying no. They're saying no through silence. Delay is rejection with plausible deniability. Delay is the deadliest form of denial. That's Parkinson's law of delay. Not the same as the original Parkinson's law about work expansion. This one's about decisions. When people don't want to approve something but don't want to explicitly reject it, they delay. The proposal gets stuck in review, waiting for more information, pending further consideration, indefinitely. And indefinitely means no. Just slowly. The mechanism is conflict avoidance. Saying no creates confrontation. You have to justify the rejection, face disappointment, handle pushback. Delaying avoids that. You don't have to say no. You just don't say yes. The requester keeps hoping. You keep stalling. Eventually, they give up or the situation changes. The delay accomplished the rejection without the confrontation. Parkinson's law of delay explains bureaucratic paralysis. Proposals that threaten the status quo don't get rejected outright. They get delayed, sent to committees, flagged for additional review. Each delay is procedurally justified. But collectively, they're a strategy. Delay until the proposer loses momentum. Delay until budget cycles shift. Delay until leadership changes. The delay is the decision. The process is the refusal. The law shows up in corporate politics. You pitch an idea to your boss. They say it's interesting. They'll think about it. Weeks later, nothing. You ask again. They need to discuss it with others. More weeks. Still nothing. The answer is no. They're just not saying it. Because saying no might upset you. Might create conflict. Easier to delay. Let the idea die from neglect instead of opposition. This is why aggressive follow-up matters. Delay relies on passivity. If you keep pushing, delay becomes unsustainable. Eventually, they have to give a real answer. Yes or no. But most people don't push. They take "we're still considering it" at face value. And the delay wins. The proposal dies quietly, without ever being officially killed. Parkinson's law of delay also creates asymmetric power. The person with decision authority controls the timeline. They can delay indefinitely. The person waiting for the decision has no leverage. They can ask. They can follow up. But they can't force a decision. So delay becomes a veto, one that never has to be explicitly exercised. The law is brutal. If you're waiting for a decision and it's taking too long, you probably already have your answer. It's no. The delay is the delivery mechanism. Real yes decisions happen quickly. People are excited. They move fast. No decisions get delayed, because delay is easier than confrontation, and time kills what rejection might revive. Iron Law of Oligarchy. The movement starts with ideals, equality, democracy, power to the people. Everyone participates. Everyone has a voice. It's pure, then it grows. Coordination becomes necessary. Leaders emerge. They're just organizers at first, facilitators, but they control communication. They set agendas. They make decisions when consensus is slow. Gradually, power concentrates. The leaders aren't just facilitators anymore. They're the authority. The democratic movement has become an oligarchy, and it happened without anyone deciding to abandon the principles. It just happened. Every organization, no matter how democratic its beginnings, eventually develops into an oligarchy. That's the iron law of oligarchy. Start with equality. End with hierarchy. The pattern is structural, not moral failure, not betrayal. Just inevitable dynamics. Democracy at scale is unstable. Oligarchy is the equilibrium. The mechanism is specialization. Large organizations need coordination. Coordination requires dedicated roles. The people in those roles develop expertise. They know the details. They control information flow. Members who aren't in those roles don't have the time or knowledge to participate equally. So they defer. The specialists make decisions. Over time, the specialists become a class. The oligarchs. Power concentrates because the structure demands it. The Iron Law explains why revolutionary movements become authoritarian. They overthrow the old hierarchy in the name of equality. Then they need to organize. Structure emerges. Leaders consolidate power to coordinate the movement. What began as liberation becomes a new regime. Not because the revolutionaries were insincere. Because organizational dynamics pull toward concentration. The law operates independent of intention. The law shows up in democracies. Political parties claim to represent the people. But power lies with party leadership. Donors, political operatives, the base votes. But the insiders decide who's on the ballot, what policies get prioritized, how resources get allocated. The members think they have power. The oligarchs actually have it. And the structure ensures it stays that way. Labor unions follow the same pattern, created to give workers collective power. But union leadership becomes a separate class. They negotiate. They control strike decisions. They manage the organization. Rank and file members lose influence. The union still claims to serve workers. But the oligarchs run it. The Iron Law converted democratic collective action into hierarchical administration. The law isn't cynicism. It's observation. Michels, who formulated it, studied socialist parties. Organizations explicitly committed to equality. And even they couldn't escape the pattern. Size and complexity demand coordination. Coordination creates specialists. Specialists become elites. Elites entrench. The cycle is structural. You can't organize your way out of it. This doesn't mean abandon organization. It means recognize the tendency. Build in checks. Rotate leadership. Decentralize power. Make information transparent. Limit terms. Create accountability. You can slow the Iron Law. Resist it. But you can't eliminate it. The pull toward oligarchy is constant. And without active countermeasures, it wins. Every time. Dunbar's number. You know a lot of people. Hundreds. Maybe thousands if you count social media. But how many do you actually know? Not recognize. Not follow. Actually know. Their life, their context. Your relationship with them. Probably not that many. Maybe 150. Maybe fewer. That's not random. It's a limit. Your brain can only maintain so many real relationships. Past that, people become acquaintances. Names. Faces. Not connections. The number of stable relationships a person can maintain is about 150. That's Dunbar's number. It's not exact. Some people manage more. Some fewer. But the average clusters around 150. That's the cognitive ceiling for relationship tracking. Names. Histories. Social obligations. Emotional bonds. Past 150, your brain can't keep up. Relationships degrade to shallow recognition. The depth disappears. The mechanism is cognitive capacity. Maintaining a relationship requires remembering context, who they are, what they care about, your shared history. That takes processing power. Your brain has limits. Around 150 relationships fit within those limits. Add more, and something has to give. Older relationships fade. New ones stay superficial. The total active count stays roughly constant. Because the capacity is fixed. Dunbar's number explains organizational structure. Companies under 150 people function differently than larger ones. Everyone knows everyone. Communication is informal. Trust is personal. Past 150, that breaks down. You don't know half the people. Formal processes replace informal coordination. Hierarchy becomes necessary. The shift isn't about management philosophy. It's about cognitive limits. The organization outgrew relationship-based operation. The number shows up in military units. Effective fighting units historically cluster around 150. Roman centuries. Modern companies. That size allows commanders to know their soldiers. Soldiers to know each other. Trust forms through personal connection. Scale past that, and cohesion requires different mechanisms. Rules. Hierarchy. Formal command. Because personal relationships can't span the gap. Social media breaks Dunbar's number. You have thousands of followers, hundreds of friends, but you can't maintain real relationships with them all. So the relationships hollow out. Shallow engagement. Likes. Shares. No depth. The platform created the illusion of expanded social capacity, but the cognitive limit didn't change. You still only truly know about 150 people. The rest are parasocial, one-directional, or dormant. Dunbar's number also reveals why communities fracture. Online groups start small. Everyone knows everyone. Then they grow. Past 150, the community field breaks. Subgroups form. Cliques. Because you can't maintain connection with everyone. So you maintain it with some. The community fragments not from conflict but from scale. The limit was exceeded. Cohesion became impossible. The number isn't prescriptive. It's descriptive. You can't force more relationships by trying harder. The limit is structural. Cognitive capacity. Time allocation. Emotional bandwidth. You have about 150 slots. Fill them wisely. Because everyone else is noise. Not because they're unimportant. Because your brain can't hold them in the relationship space. The number is the number. And it's been the number for as long as humans have been human.